Quantum mechanics is where our journey into the microscopic universe begins. It's a revolutionary branch of physics that explores the bizarre behavior of atoms, electrons, and the fundamental particles that shape our reality, first formulated in the early 20th century by pioneering scientists like Max Planck and Niels Bohr. Imagine it as the physics of the impossibly small, the reason why atoms stay stable, why light can behave both as a wave and a particle, and why certain aspects of our universe seem to defy common sense. At its heart, quantum mechanics reveals a world radically different from our everyday experience. Here, particles can exist in multiple places simultaneously. Information can be instantly transmitted across vast distances through quantum entanglement, and the mere act of observing a system can fundamentally change its behavior. It's as if we've discovered a hidden layer of reality operating beneath the familiar world of classical physics. Think about turning on a light switch. In our everyday world, this seems simple enough. Electricity flows through wires, reaches the bulb, and illuminates the room. But quantum mechanics shows us something far more fascinating happening at the microscopic level. Inside the wire, countless electrons are moving in ways that would seem impossible in our macro world. They tunnel through barriers they shouldn't be able to cross, exist in probabilistic clouds rather than definite positions, and interact with each other through quantum fields that permeate all of space. The principles of quantum mechanics challenge our most basic assumptions about reality. Unlike classical physics, where we can precisely predict the path of a thrown ball or the orbit of a planet, quantum mechanics deals in probabilities. It tells us that we can never simultaneously know both the exact position and momentum of a particle. This is the famous uncertainty principle discovered by Werner Heisenberg. It's not just a limitation of our measuring devices, it's a fundamental property of nature itself. Consider an electron orbiting an atomic nucleus. Classical physics would tell us it should spiral into the nucleus, causing atoms to collapse. But quantum mechanics reveals why this doesn't happen. Electrons exist in discrete energy levels, or quantum states, and can only jump between these states by absorbing or emitting specific amounts of energy. This quantization of energy, first proposed by Max Planck to explain black body radiation, is what gives quantum mechanics its name and helps explain the stability of matter itself. Perhaps most remarkably, quantum mechanics has shown us that particles can become entangled, creating instantaneous connections that seem to transcend space and time. Einstein famously called this spooky action at a distance, unable to reconcile it with his theory of relativity. Yet experiments have repeatedly confirmed this strange phenomenon, which is now being harnessed for revolutionary technologies like quantum computers and unbreakable encryption systems. As we delve deeper into quantum mechanics, we'll explore how these microscopic phenomena give rise to the macroscopic world we experience. We'll see how quantum effects explain why the sun shines, how photosynthesis works, and why your computer's transistors function. We'll uncover the profound philosophical implications of quantum mechanics, which suggests that reality itself might be fundamentally probabilistic rather than deterministic. From the double-slit experiment that demonstrates the wave-particle duality of matter and light, to the quantum tunneling that makes certain chemical reactions possible, we'll journey through the key experiments and discoveries that revealed this hidden quantum realm. we'll meet the brilliant minds who developed this theory, often against fierce opposition from those who couldn't accept such a radical departure from classical physics. Understanding quantum mechanics isn't just about satisfying scientific curiosity. These principles underpin much of our modern technology, from laser systems to magnetic resonance imaging, MRI machines. The next generation of computers, sensors, and communication systems will rely even more heavily on quantum effects. As we explore these concepts, we'll see how this seemingly abstract theory has profound practical applications in our daily lives. Join us as we venture into this quantum realm, where probability clouds replace definite trajectories, where particles can exist in multiple states simultaneously until observed, and where the very act of measurement shapes reality itself. Through careful explanation and vivid analogies, we'll make these abstract concepts accessible while preserving their profound implications for our understanding of the universe. Together, we'll discover how quantum mechanics has not only revolutionized our understanding of the microscopic world, but has also opened up new possibilities for technology and forced us to reconsider the very nature of reality itself. This is where our journey begins, at the boundary between the familiar classical world and the strange, fascinating realm of quantum physics. The most striking demonstration of quantum mechanics' strange nature comes from the famous double-slit experiment, first performed with light by Thomas Young in 1801, but later revealing profound implications for our understanding of all matter and energy. In this deceptively simple experiment, individual particles are fired at a screen with two parallel slits. Classical physics would predict these particles behave like tiny bullets, creating two distinct bands on the detector behind the slits. Instead, something extraordinary happens. When particles pass through the slits, they create an interference pattern, alternating bands of high and low intensity, exactly like waves rippling through water. Even more bizarrely, this pattern emerges even when particles are fired one at a time, as if each particle somehow travels through both slits simultaneously, interfering with itself. This wave-particle duality challenges our fundamental understanding of reality, suggesting that particles exist as waves of probability until they are observed or measured. To appreciate the profound implications of this experiment, imagine throwing pebbles into a pond. You'd expect to see two distinct sets of ripples where the pebbles hit the water. But in the quantum world, a single particle behaves as if it's creating interference patterns with itself, like a pebble, somehow landing in two places at once. This phenomenon isn't just a curious laboratory observation. It represents a fundamental aspect of how all matter and energy behave at the quantum level. The mystery deepens when we attempt to observe which slit the particle passes through. Place a detector at either slit, and the interference pattern vanishes, replaced by the classical pattern of two distinct bands. It's as if the mere act of observation forces the particle to choose a definite path, collapsing the wave of probability into a specific reality. This observation effect lies at the heart of quantum mechanics' most puzzling aspects, suggesting that consciousness and reality are more deeply intertwined than we ever imagined. This brings us to one of quantum mechanics' most contentious features, the role of measurement and observation. In classical physics, measurement simply reveals pre-existing properties of a system. But in quantum mechanics, the act of measurement actively participates in determining reality. Before measurement, quantum systems exist in a superposition of all possible states, Schrödinger's famous cat, simultaneously alive and dead until the box is opened and observation forces a single outcome. Consider the implications. Particles don't have definite properties until they're measured. An electron's position, momentum, or spin exists only as a range of probabilities until observation collapses these possibilities into specific values. This isn't a limitation of our measuring devices or understanding. It's a fundamental feature of reality itself. The mathematics of quantum mechanics through the Schrödinger equation precisely describes these probability waves, but can only predict the likelihood of different outcomes, never a single definite result. This probabilistic nature of quantum mechanics troubled many physicists, including Einstein, who famously declared, "God does not play dice with the universe." Yet every experiment has confirmed quantum mechanics predictions with unprecedented accuracy. The theory's mathematical framework, though abstract, provides the most precise descriptions of nature ever developed by science. The implications extend far beyond laboratory curiosities. Quantum superposition and interference are essential to understanding chemical bonds, the structure of DNA, and even the process of photosynthesis. When electrons in atoms transition between energy levels, they don't simply jump from one state to another. They exist briefly in a superposition of states, following all possible paths simultaneously before settling into their final configuration. These quantum effects, though typically observed only at microscopic scales, occasionally manifest in macroscopic phenomena. Superconductivity, where electrical resistance completely vanishes at low temperatures, results from electrons forming quantum entangled pairs that move in perfect coordination. Similar quantum effects enable the precise atomic clocks that make GPS navigation possible and form the basis for emerging technologies like quantum computers. Understanding these quantum phenomena requires us to abandon many intuitive notions about reality. Particles don't follow definite trajectories, but exist as waves of possibility. Information about quantum states can be instantaneously correlated across vast distances through entanglement. The very act of observation shapes the reality we observe. These concepts might seem to contradict common sense, but they represent our most accurate description of nature at its most fundamental level. As we continue our journey into quantum mechanics, we'll explore how these basic principles give rise to even more extraordinary phenomena. We'll see how quantum tunneling allows particles to pass through seemingly impenetrable barriers, how quantum entanglement enables new forms of computation and communication, and how the quantum vacuum itself seethes with virtual particles popping in and out of existence. Each discovery reveals another layer of the profound mystery at the heart of physical reality. 2. Quantum entanglement, perhaps the most mysterious aspect of quantum mechanics, demonstrates what Einstein called spooky action at a distance. When two particles become entangled, their quantum states are linked regardless of the distance between them. Measuring one particle instantly determines the state of its entangled partner, even if they're separated by the width of the universe. This seemingly instantaneous communication appears to violate Einstein's special relativity, which states that nothing can travel faster than light. Preparing and narrating this theory took us a lot of time. So if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the theory. To understand entanglement, imagine two coins that always land oppositely. When one shows heads, the other invariably shows tails. But in the quantum realm, these coins exist in a superposition of both states until observed. The moment you look at one coin, you instantly know the state of the other, no matter how far apart they are. However, this isn't classical communication. You can't use entanglement to send messages faster than light. The correlation between particles is intrinsic to their shared quantum state. The implications of quantum entanglement extend far beyond theoretical physics. Scientists now use entangled particles to develop quantum computers, which could potentially solve certain problems exponentially faster than classical computers. In quantum cryptography, entangled particles create unbreakable encryption keys. Any attempt to intercept the communication disrupts the entanglement, immediately alerting users to the breach. These applications represent just the beginning of a technological revolution based on quantum principles. At the heart of quantum mechanics lies another fascinating phenomenon: quantum tunneling. Classical physics tells us that a ball rolling up a hill will roll back down if it lacks sufficient energy to reach the top. But in the quantum world, particles can occasionally tunnel through barriers they shouldn't be able to cross. It's as if a person walking into a solid wall occasionally emerges on the other side, defying our classical understanding of reality. This tunneling effect isn't just a theoretical curiosity, it's essential to numerous natural processes. The sun's nuclear fusion reactions rely on quantum tunneling, allowing protons to overcome their mutual electrical repulsion and fuse into helium nuclei. Without this quantum effect, stars couldn't shine. Similarly, quantum tunneling enables certain types of radioactive decay and plays a crucial role in photosynthesis, where energy from sunlight is converted into chemical energy in plants. Modern technology also harnesses quantum tunneling. Scanning tunneling microscopes use this effect to create detailed images of individual atoms on surfaces. Tunnel diodes in electronic devices exploit quantum tunneling to control electrical current. Even the flash memory in our computers and smartphones relies on electrons tunneling through insulating barriers to store and retrieve information. The quantum vacuum, far from being empty space, constantly bubbles with activity at the microscopic level. According to quantum field theory, pairs of virtual particles continuously pop into and out of existence, borrowing energy from the vacuum for incredibly brief moments before annihilating each other. These quantum fluctuations have measurable effects, such as the Casimir force between closely spaced metal plates, and may have played a crucial role in the early universe's expansion. These virtual particles aren't just theoretical constructs. They have real, observable effects. When virtual particles appear near a black hole's event horizon, one member of the pair might fall in, while the other escapes, becoming real and carrying away energy. This process, known as Hawking radiation, suggests that black holes slowly evaporate over time, linking quantum mechanics with gravity in unexpected ways. The role of consciousness in quantum mechanics remains one of its most debated aspects. The Copenhagen interpretation, long the standard view among physicists, suggests that consciousness itself plays a role in collapsing quantum superpositions into definite states. Alternative interpretations, like the many worlds interpretation, propose that every possible quantum outcome occurs in parallel universes, avoiding the need for conscious observers, but introducing its own philosophical challenges. These interpretations aren't just philosophical musings. They reflect deep questions about the nature of reality itself. Does consciousness play a fundamental role in shaping physical reality? Do parallel universes exist? How can we reconcile quantum mechanics' probabilistic nature with our apparent experience of a definite classical world? These questions continue to challenge our understanding of the relationship between mind, matter, and measurement. Recent experiments have pushed the boundaries of quantum mechanics into increasingly macroscopic systems. Scientists have created quantum superpositions in larger and larger molecules, demonstrated quantum entanglement between distant atoms, and even explored quantum effects in biological systems. These experiments suggest that the boundary between the quantum and classical worlds might be more fluid than previously thought. As we delve deeper into quantum mechanics, each answer seems to raise new questions. The theory's mathematical framework makes incredibly accurate predictions, yet its philosophical implications remain hotly debated. What seems clear is that quantum mechanics reveals a reality far stranger and more interconnected than our everyday experience suggests. A world where probability waves guide particle behavior, where consciousness might shape physical reality, and where the very fabric of space-time teems with virtual particles. Quantum field theory represents our deepest understanding of how particles and forces interact at the fundamental level. Unlike earlier quantum mechanics, which treated particles as point-like objects moving through space, quantum field theory sees particles as excitations in underlying fields that permeate all of space and time. Imagine a calm lake. The surface represents a quantum field, and waves on that surface represent particles. Just as waves can appear anywhere on the lake's surface, particles can emerge from their corresponding fields at any point in space. These quantum fields are the true fundamental entities of nature. Every type of particle, electrons, photons, quarks, has its own corresponding field. When we observe particles, we're actually detecting ripples or excitations in these ever-present fields. The strength of these ripples determines the particle's energy, while their patterns of oscillation determine properties like spin and charge. This perspective revolutionizes our understanding of particle interactions, showing them as exchanges of energy between interlinked fields rather than collisions between discrete objects. The implications of quantum field theory extend far beyond simple particle physics. The theory explains how forces work at the quantum level. The electromagnetic force, for instance, arises from the exchange of photons between charged particles. These force-carrying particles, or bosons, can be thought of as disturbances propagating through their respective fields, mediating interactions between matter particles. The mathematics of quantum field theory precisely describes these interactions, leading to predictions that match experimental observations with unprecedented accuracy. One of the most striking predictions of quantum field theory is the existence of antiparticles, mirror images of normal particles with opposite properties. When enough energy is available, particle-antiparticle pairs can spontaneously emerge from the quantum vacuum, existing briefly before annihilating each other in a burst of pure energy. This process isn't just theoretical. It happens constantly in the vacuum of space, and these virtual particles have measurable effects on the properties of atoms and the strength of forces. Consider the electron's magnetic moment, a measure of its intrinsic magnetism. Quantum field theory predicts that virtual particles popping in and out of existence should slightly modify this value from what simpler theories suggest. When scientists measured the electron's magnetic moment, they found it matched the quantum field theory prediction to an astounding 12 decimal places, one of the most precise confirmations of any scientific theory in history. The theory also reveals the deep connection between matter and energy, embodied in Einstein's famous equation E equals mc squared. In quantum field theory, this equivalence becomes manifest. Sufficient energy concentrated in a field can create particles of matter, while matter can be converted back into pure energy. This process occurs naturally in particle accelerators, where colliding beams of particles create new, more massive particles from pure energy, allowing scientists to study the fundamental building blocks of nature. Perhaps most remarkably, quantum field theory shows how the seemingly empty vacuum of space is actually a complex, dynamic system. The quantum vacuum isn't truly empty, but filled with fields in their lowest energy states, constantly fluctuating and producing virtual particles. These vacuum fluctuations have real, measurable consequences. They contribute to the energy levels of atoms, affect the strength of forces, and may even influence the expansion of the universe itself. The theory's success extends to explaining phenomena that were mysterious in earlier frameworks. Superconductivity, where electrical resistance vanishes at low temperatures, emerges naturally from the quantum field description of electrons interacting with crystal lattices. The strong nuclear force, which binds quarks together in atomic nuclei, is elegantly described by quantum chromodynamics, a quantum field theory of the strong interaction. Yet, challenges remain. Quantum field theory works brilliantly for 3 of the 4 fundamental forces: electromagnetic, strong, and weak, but struggles to incorporate gravity. Attempts to treat gravity as a quantum field lead to mathematical infinities that can't be resolved using standard techniques. This incompatibility between quantum field theory and gravity remains one of physics' greatest unsolved problems, suggesting we may need an even deeper theory to fully understand nature at its most fundamental level. The theory also raises philosophical questions about the nature of reality. If particles are really excitations in fields, what are these fields made of? Are they mathematical abstractions or physical entities? The success of quantum field theory in describing nature suggests these fields are, in some sense, real, but their true nature remains mysterious. The theory challenges our intuitive notions of emptiness and substance, suggesting that what we perceive as empty space is actually a rich, dynamic medium underlying all of reality. As we continue exploring quantum physics, we'll see how these field concepts lead to even more extraordinary insights. We'll discover how the Higgs field gives particles their mass, how quantum fields might have driven cosmic inflation in the early universe, and how the interplay of various fields determines the fundamental structure of matter. Each discovery reveals another layer of the profound interconnectedness of nature at its deepest levels. The Higgs field and its associated particle, the Higgs boson, represent one of modern physics' greatest triumphs. Unlike other quantum fields, the Higgs field permeates all of space, with a non-zero value even in its lowest energy state, creating what physicists call a vacuum expectation value. This seemingly technical detail has profound consequences. It's what gives particles their mass. Imagine moving through a pool of honey. Different objects experience different amounts of resistance. Similarly, particles moving through the Higgs field experience different degrees of interaction, which manifests as their mass. The discovery of the Higgs boson at CERN's Large Hadron Collider in 2012 marked a watershed moment in physics. This particle, often called the God particle, much to physicists' chagrin, represents excitations in the Higgs field, just as photons represent excitations in the electromagnetic field. But creating these excitations requires enormous energy. The Large Hadron Collider smashes protons together at nearly the speed of light, briefly recreating conditions similar to those just after the Big Bang. Understanding the Higgs mechanism reveals deeper insights into the universe's structure. In the extreme heat of the early universe, the Higgs field had a value of 0, and all particles were massless, moving at the speed of light. As the universe cooled, the Higgs field settled into its current non-zero value, giving particles their characteristic masses through a process called spontaneous symmetry breaking. This transition, known as the electroweak phase transition, was crucial in shaping the universe we observe today. The success of the standard model of particle physics, which includes the Higgs mechanism, represents both a triumph and a puzzle. While it perfectly describes the behavior of matter and 3 of the 4 fundamental forces, it leaves key questions unanswered. Why do particles have the exact masses we observe? Why is gravity so much weaker than the other forces? These questions suggest there might be deeper principles yet to discover. One potential answer lies in supersymmetry, a theoretical extension of the standard model that proposes every known particle has a heavier partner particle. These superpartners could explain dark matter, the mysterious substance that makes up about 85% of the universe's matter. Though we haven't detected any superpartners yet, they might be too heavy to create in current particle accelerators, requiring even more powerful machines to discover. The search for these new particles connects to another fascinating area, the quantum nature of gravity. While general relativity describes gravity as curved space-time, quantum mechanics suggests it should be mediated by particles called gravitons. However, attempts to detect gravitons or quantize gravity lead to mathematical infinities that have resisted resolution for decades. This incompatibility between quantum mechanics and gravity represents one of physics' greatest unsolved problems. String theory offers one potential solution, suggesting that all particles are actually tiny vibrating strings in multiple dimensions. Different vibrational patterns of these strings would create different particles, including gravitons, naturally unifying gravity with quantum mechanics. However, string theory requires extra spatial dimensions beyond the 3 we observe, curled up so tightly they're invisible to current experiments. While mathematically elegant, the theory remains controversial due to the difficulty of testing its predictions. Loop quantum gravity provides an alternative approach, proposing that space itself is quantized into tiny, discrete units at the Planck scale. In this view, space-time isn't a smooth continuum, but a complex network of quantum atoms of space, connected by lines of force. This discrete structure would naturally prevent the infinities that plague attempts to quantize gravity, while reproducing Einstein's smooth space-time at larger scales. These theories hint at an even deeper reality underlying quantum mechanics and gravity. The holographic principle inspired by black hole physics suggests that all the information in a region of space might be encoded on its boundary like a three-dimensional image stored on a two-dimensional hologram. This principle has profound implications for our understanding of space, time, and information at the quantum level. Recent developments in quantum gravity research have focused on the role of quantum entanglement in space-time structure. Some physicists propose that entanglement between quantum degrees of freedom might be responsible for weaving the fabric of space-time itself. This perspective suggests that space and time might emerge from more fundamental quantum phenomena, rather than serving as a pre-existing backdrop for physical events. These investigations push the boundaries of our understanding, suggesting that reality at its most fundamental level might be radically different from our everyday experience. The discrete nature of space, proposed by loop quantum gravity, the extra dimensions of string theory, and the holographic encoding of information challenge our basic intuitions about the nature of reality. As we probe these depths, we find that each answer reveals new questions. The quantum nature of gravity, the origin of particle masses, the structure of space-time. These mysteries continue to drive theoretical physics forward. Yet the very difficulty of these questions and the ingenuity required to approach them reveals the profound beauty and complexity of the universe at its most fundamental level. The nature of time at the quantum level presents one of physics' most perplexing puzzles. In our everyday experience, time flows steadily forward, creating a clear distinction between past, present, and future. But quantum mechanics and relativity suggest a more complex picture. At the quantum scale, time becomes fuzzy and uncertain, bound by Heisenberg's uncertainty principle, just like position and momentum. This quantum nature of time raises profound questions about causality and the arrow of time itself. The Wheeler-DeWitt equation, often called the wave function of the universe, attempts to describe quantum mechanics in a way that includes gravity. Surprisingly, this equation contains no explicit time variable, suggesting that, at the most fundamental level, time might be an emergent phenomenon rather than a basic ingredient of reality. This problem of time in quantum gravity has led physicists to question whether our perception of time's flow might be an illusion arising from the way quantum systems interact. Consider a quantum particle's path through space and time. According to Richard Feynman's path integral formulation, the particle doesn't follow a single trajectory, but simultaneously takes all possible paths between its starting and ending points. These paths can even include those where time appears to run backward, challenging our intuitive notion of temporal sequence. The final probability of any particular outcome emerges from the interference of all these possible histories. This quantum view of time connects to another fascinating concept: quantum decoherence. As quantum systems interact with their environment, their delicate superpositions of states become entangled with countless environmental particles. This process effectively records information about the system in its surroundings, creating what appears to us as an irreversible sequence of events. Decoherence might explain why we experience time as flowing in one direction, even though the fundamental laws of physics are time-symmetric. The relationship between time and entropy adds another layer of complexity. The second law of thermodynamics states that entropy, roughly the measure of disorder in a system, tends to increase over time. This thermodynamic arrow of time aligns with our experience of irreversible processes, like a broken egg that can't spontaneously reassemble itself. But in quantum mechanics, the underlying processes are reversible. The apparent contradiction between quantum reversibility and thermodynamic irreversibility remains a deep mystery. Black holes provide a unique laboratory for studying these temporal paradoxes. Near a black hole's event horizon, extreme gravitational effects cause time to slow dramatically relative to distant observers. Quantum mechanics suggests that black holes slowly evaporate through Hawking radiation. But this process raises troubling questions about information preservation. If a black hole contains quantum information about the particles that fell into it, what happens to this information when the black hole evaporates? The black hole information paradox has led to radical proposals about the nature of space-time. The holographic principle suggests that all the information about a region of space, including its temporal evolution, might be encoded on its boundary. This would mean that time itself might be an emergent property arising from more fundamental relationships between quantum states on this holographic boundary. Recent theoretical work has explored the possibility that space-time might be built from quantum entanglement. In this view, the very fabric of space and time emerges from patterns of quantum correlations between fundamental degrees of freedom. Time's flow would then be a manifestation of how these quantum correlations evolve and propagate, rather than an independent dimension of reality. This quantum reconstruction of space-time connects to ideas in quantum computing and information theory. Some physicists propose that space, time, and gravity might be emergent phenomena arising from more fundamental quantum information processing at the Planck scale. In this picture, what we perceive as the flow of time might be analogous to the execution of a vast quantum computation. The implications extend beyond pure physics into questions of consciousness and free will. If time at the quantum level is fuzzy and partially reversible, how does our conscious experience of a definite temporal sequence arise? Some theories suggest that consciousness itself might play a role in the emergence of classical reality from quantum possibilities, including our perception of time's forward flow. These investigations have practical implications for quantum technologies. Understanding the quantum nature of time could lead to more precise atomic clocks, better quantum computers, and new approaches to quantum cryptography. The very features that make quantum time puzzling, superposition, entanglement, and interference, might become resources for future technologies. The study of time at the quantum level reveals a reality far stranger than our everyday experience suggests. From the timeless Wheeler-DeWitt equation to the emergence of temporal order through decoherence, from black hole paradoxes to holographic space-time, we find that time itself might not be the fundamental entity we once assumed. Instead, it might emerge from deeper quantum phenomena, just as temperature emerges from the collective behavior of countless atoms. As we probe these temporal mysteries, we're led to question not just the nature of time, but the very structure of reality itself. The interplay between quantum mechanics, gravity, and time continues to challenge our understanding, suggesting that the universe might be organized in ways far more subtle and interconnected than classical physics imagined. The intersection of quantum mechanics and thermodynamics reveals profound insights about the nature of information, energy, and the arrow of time. Classical thermodynamics, developed in the 19th century to understand steam engines, takes on new meaning when viewed through the lens of quantum mechanics. At the quantum level, thermodynamic concepts like heat, work, and entropy become intertwined with quantum phenomena like superposition and entanglement. Consider the fundamental concept of entropy, traditionally viewed as a measure of disorder or randomness in a system. Quantum mechanically, entropy takes on a more precise meaning related to information and quantum states. The von Neumann entropy, which describes the quantum state of a system, connects thermodynamic entropy with quantum information theory. This connection suggests that information isn't just an abstract concept, but a physical quantity governed by the laws of quantum mechanics. Quantum fluctuations in vacuum energy demonstrate this relationship between quantum mechanics and thermodynamics. The quantum vacuum, far from being empty, seethes with virtual particles popping in and out of existence. These fluctuations carry energy and entropy, contributing to the thermodynamic properties of space itself. The Casimir effect, where parallel metal plates experience a tiny attractive force due to vacuum fluctuations, provides experimental evidence for these quantum thermodynamic phenomena. The quantum version of Maxwell's demon, a thought experiment challenging the second law of thermodynamics, illustrates the deep connection between information and energy. In the quantum realm, the demon's ability to sort particles based on their properties is limited by quantum measurement and uncertainty. The energy cost of acquiring information about quantum states exactly balances any potential violation of the second law, preserving thermodynamic principles even in quantum systems. Quantum heat engines, operating at the nanoscale, reveal new aspects of energy conversion. Unlike classical heat engines, quantum engines can exploit quantum coherence and entanglement to achieve higher efficiencies. However, quantum uncertainty and measurement effects introduce fundamental limits to their performance. These quantum thermodynamic devices might find applications in nanoscale technologies, from quantum computers to molecular machines. The thermodynamic arrow of time gains new significance in quantum systems. While individual quantum processes are reversible, interactions with the environment lead to decoherence, the loss of quantum coherence that makes macroscopic processes appear irreversible. This quantum to classical transition helps explain how time's arrow emerges from time-symmetric quantum laws, connecting microscopic reversibility with macroscopic irreversibility. Quantum entanglement plays a crucial role in thermodynamic processes. When particles become entangled, their thermal properties become correlated in ways impossible in classical physics. This quantum thermalization process differs fundamentally from classical heat exchange, leading to new possibilities for energy transfer and thermal management in quantum systems. The study of quantum thermodynamics extends to black holes, where extreme gravitational fields meet quantum effects. Hawking radiation, the thermal emission from black holes demonstrates a deep connection between gravity, quantum mechanics, and thermodynamics. The entropy of a black hole proportional to its surface area rather than its volume hints at the holographic nature of information in quantum gravity. Recent experiments have begun probing these quantum thermodynamic effects in laboratory settings, ultra-cold atomic systems, where quantum effects dominate thermal behavior, allow scientists to study how quantum systems approach thermal equilibrium. These experiments reveal subtle quantum effects in thermalization processes, challenging our understanding of how isolated quantum systems evolve. The role of measurement in quantum thermodynamics raises fundamental questions about the nature of observation and entropy. Each measurement of a quantum system introduces disturbance, increasing the system's entropy. This measurement-induced entropy production connects to broader questions about the role of observers in quantum mechanics and the emergence of classical reality from quantum phenomena. Quantum phase transitions occurring at absolute zero temperature represent a purely quantum form of matter organization. Unlike classical phase transitions driven by thermal fluctuations, quantum phase transitions are driven by quantum fluctuations in the ground state. These transitions reveal new states of matter and new mechanisms for organizing quantum systems. The principles of quantum thermodynamics find practical applications in quantum computing. Quantum error correction, essential for building practical quantum computers, must contend with thermal noise and decoherence. Understanding how quantum systems interact with their thermal environment is crucial for developing robust quantum computing technologies. Environmental decoherence, the process by which quantum systems lose their quantum properties through interaction with their surroundings, represents a key interface between quantum and classical thermodynamics. This process explains how quantum systems come to exhibit classical behavior, providing a bridge between the quantum and classical worlds. The study of quantum thermodynamics continues to reveal new phenomena and challenge our understanding of nature's fundamental laws, from nanoscale heat engines to cosmological phenomena, from quantum computers to black holes. The interplay between quantum mechanics and thermodynamics shapes our understanding of the physical world at its most fundamental level. As we develop new technologies operating at the quantum scale, understanding these quantum thermodynamic principles becomes increasingly important. The ability to control and manipulate quantum systems while managing their thermal properties will be crucial for future technological developments in quantum computing, quantum sensing, and quantum communication. The quantum nature of information stands as one of the most revolutionary insights of modern physics. Unlike classical information, which exists in definite states of 0 or 1, quantum information can exist in superpositions of multiple states simultaneously. This fundamental difference leads to entirely new ways of processing and transmitting information, with profound implications for computation, communication, and our understanding of reality itself. Quantum bits, or qubits, form the basic unit of quantum information. While a classical bit must be either 0 or 1, a qubit can exist in a superposition of both states at once. Imagine a coin spinning on a table. Before it lands, it's in a kind of superposition of heads and tails. Quantum superposition is similar but more profound, as the qubit genuinely exists in multiple states simultaneously until measured. This property allows quantum computers to perform certain calculations exponentially faster than classical computers. The phenomenon of quantum entanglement adds another layer to quantum information theory. When qubits become entangled, their quantum states become correlated in ways impossible for classical bits. Einstein called this spooky action at a distance, but it's now understood as a fundamental feature of quantum information. Entanglement allows for new forms of communication and computation that have no classical counterpart. Consider quantum teleportation, a process that uses entanglement to transmit quantum information between locations. Despite its science fiction-sounding name, quantum teleportation is a real phenomenon, demonstrated in laboratories worldwide. It doesn't transport matter itself, but rather transmits the complete quantum state of a particle to another location through entanglement and classical communication. The no-cloning theorem represents a fundamental limitation in quantum information theory. Unlike classical information, which can be perfectly copied, quantum information cannot be cloned without destroying the original state. This limitation, while seemingly restrictive, enables quantum cryptography, methods of communication that are theoretically impossible to hack because any attempt to intercept the information necessarily disturbs it in a detectable way. Quantum error correction presents one of the greatest challenges in quantum information processing. Quantum states are incredibly fragile, easily disturbed by interaction with their environment through a process called decoherence. Scientists have developed sophisticated error correction codes that protect quantum information by encoding it across multiple physical qubits, allowing quantum computations to proceed even in the presence of noise and errors. The concept of quantum supremacy, the point at which a quantum computer can perform calculations beyond the capability of any classical computer, represents a milestone in quantum information processing. In 2019, Google claimed to achieve quantum supremacy with their Sycamore processor, though debate continues about the practical significance of this achievement. The race to develop practical quantum computers continues, with different approaches competing to create stable, scalable quantum systems. Quantum information theory has profound implications for our understanding of black holes and the nature of space-time itself. The holographic principle, inspired by studies of black hole entropy, suggests that the information content of a region of space might be encoded on its boundary, like a three-dimensional image stored on a two-dimensional hologram. This principle hints at deep connections between quantum information, gravity, and the structure of space-time. The field of quantum metrology shows how quantum information can be used to achieve unprecedented precision in measurements. By exploiting quantum entanglement and superposition, scientists can develop sensors far more sensitive than classical devices. These quantum sensors could revolutionize everything from medical imaging to navigation systems, detecting tiny changes in gravity, magnetic fields, or other physical quantities. Quantum random number generation represents another practical application of quantum information theory. Unlike classical random number generators, which are actually pseudo-random, quantum systems can generate truly random numbers based on fundamental quantum uncertainty. These random numbers are crucial for cryptography, scientific simulations, and other applications requiring unpredictable sequences. The quantum internet, a network that would transmit quantum information between distant locations, represents the next frontier in quantum information technology. Such a network would enable secure communication, distributed quantum computing, and new forms of quantum sensing. While significant technical challenges remain, prototype quantum networks are already being developed and tested. The relationship between quantum information and thermodynamics reveals deep connections between information, energy, and entropy. Landauer's principle states that erasing information requires a minimum amount of energy, linking information directly to physical reality. This connection suggests that information might be as fundamental as matter and energy in our understanding of the universe. Quantum information theory also provides new perspectives on the measurement problem in quantum mechanics. The process of measurement, where quantum superpositions collapse into definite states, can be understood as information transfer from the quantum system to the measuring apparatus. This information-theoretic approach to quantum measurement might help resolve some of the philosophical puzzles surrounding quantum mechanics. As we develop more sophisticated quantum technologies, the principles of quantum information theory become increasingly important for practical applications. From quantum computers that could revolutionize drug discovery and material science, to quantum sensors that could detect underground resources or predict earthquakes, the ability to manipulate quantum information opens new possibilities for technology and scientific discovery. The study of quantum information continues to reveal surprising connections between seemingly disparate areas of physics and computation. As we probe deeper into the nature of quantum information, we may find that information itself is a fundamental building block of reality, shaping the structure of space, time, and matter at the most basic level. The marriage of quantum mechanics and cosmology reveals startling insights about the origin and evolution of our universe. Quantum cosmology attempts to describe the entire universe as a quantum system, applying the principles of quantum mechanics to cosmic scales. This approach leads to profound questions about the nature of time, space, and existence itself when viewed through the lens of quantum theory. The quantum origin of the universe presents one of the most fascinating applications of quantum cosmology. In classical general relativity, the Big Bang represents a singularity, a point where the laws of physics break down. However, quantum mechanics suggests a different picture. Just as quantum tunneling allows particles to pass through seemingly impenetrable barriers, quantum effects might have allowed the universe to emerge from nothing, a process called quantum nucleation. This quantum beginning hints at even more extraordinary possibilities. The wave function of the universe, described by the Wheeler-DeWitt equation, suggests that the early universe might have existed in a superposition of different states, much like a quantum particle can exist in multiple states simultaneously. This quantum fog would have contained all possible configurations of space, time, and matter before decoherence selected the particular universe we observe. Inflation, the theory that the universe underwent a period of exponential expansion in its earliest moments, takes on new significance when quantum effects are considered. Quantum fluctuations during this inflationary period would have been stretched to cosmic scales, seeding the density variations that eventually led to the formation of galaxies and large-scale structures we see today. Our very existence thus traces back to quantum phenomena in the infant universe. The concept of eternal inflation suggests that quantum effects might continuously spawn new universes in expanding bubbles of space-time. In this scenario, our observable universe would be just one bubble in an infinite multiverse, each with potentially different physical constants and laws. This quantum multiverse would arise naturally from the combination of inflation and quantum mechanics, though testing such theories remains a profound challenge. Quantum cosmology also offers new perspectives on the arrow of time. While quantum mechanics typically describes time-symmetric processes, our universe shows a clear temporal direction from past to future. The quantum to classical transition through decoherence might explain this emergence of time's arrow, as quantum interactions with the environment create irreversible changes that define a preferred direction of time. The role of observation in quantum cosmology raises peculiar questions. In standard quantum mechanics, measurement plays a crucial role in collapsing quantum states into definite outcomes. But who or what serves as the observer for the entire universe? Some theories suggest that decoherence through interaction between different parts of the universe effectively creates its own observations, resolving the measurement problem without requiring external observers. The holographic principle, when applied to cosmology, suggests that our three-dimensional universe might be encoded on a two-dimensional boundary, like a vast cosmic hologram. This principle emerges from studies of black hole entropy, but might apply to the entire cosmos. If true, it would mean that the fundamental description of our universe requires one fewer dimension than we observe, with profound implications for our understanding of space, time, and quantum gravity. Recent developments in loop quantum cosmology suggest that the Big Bang might have been preceded by a big bounce, where a previous contracting universe rebounded through quantum effects. This scenario avoids the classical singularity problem and suggests that our universe might be part of an endless cycle of expansion and contraction, with quantum mechanics governing the transitions between cycles. The question of cosmic consciousness adds another layer to quantum cosmology. Some interpretations of quantum mechanics assign a special role to consciousness in the measurement process. Applied to cosmology, this raises profound questions about the relationship between consciousness, observation, and the emergence of classical reality from quantum possibilities at the cosmic scale. String theory contributes to quantum cosmology through the concept of the landscape, an enormous number of possible vacuum states, each corresponding to a different universe with different physical constants. Quantum tunneling between these vacuum states might allow for the creation of new universes, suggesting a vast multiverse of possibilities, all governed by quantum mechanics at the deepest level. The anthropic principle takes on new significance in quantum cosmology. If quantum effects generate multiple universes with different properties, the fact that we observe a universe suitable for life might be a selection effect. We necessarily find ourselves in a universe compatible with our existence. This principle helps explain the apparent fine-tuning of physical constants without requiring a purposeful design. Quantum entanglement at cosmic scales might play a crucial role in the structure of space-time itself. Recent theories suggest that quantum entanglement between degrees of freedom might be responsible for weaving the fabric of space and time. This would mean that the very structure of our universe emerges from quantum correlations, with classical space-time as an emergent phenomenon. The study of quantum cosmology continues to push the boundaries of our understanding, suggesting that the universe, at its most fundamental level, operates according to quantum principles. From the quantum origin of cosmic structure to the possibility of multiple universes, from the emergence of time to the nature of space itself, quantum cosmology reveals a reality far stranger and more fascinating than classical physics ever imagined. As we develop new theoretical tools and observational techniques, we may gain deeper insights into how quantum mechanics shapes the cosmos. The quest to understand the quantum nature of the universe drives us to question our most basic assumptions about reality, leading us toward a more complete understanding of our place in the quantum cosmos. At the intersection of quantum mechanics and biological systems lies a fascinating frontier that challenges our understanding of life itself. While biological processes were long thought to occur purely in the classical realm, evidence increasingly suggests that quantum effects play crucial roles in fundamental life processes. From photosynthesis to bird navigation, from enzyme catalysis to consciousness, quantum biology reveals how nature harnesses quantum phenomena to optimize biological functions. Photosynthesis provides one of the most striking examples of quantum effects in biology. The remarkable efficiency with which plants convert sunlight into chemical energy, nearly 100% in optimal conditions, stems from quantum coherence in their light harvesting complexes. Energy captured by chlorophyll molecules travels to reaction centers through multiple paths simultaneously, using quantum superposition to find the most efficient route. This quantum walk enables plants to transfer energy with minimal loss, a feat that human-engineered solar cells have yet to match. The ability of migratory birds to navigate using Earth's magnetic field may rely on quantum entanglement. In the retinas of birds, specialized proteins called cryptochromes contain pairs of electrons that become entangled when excited by light. These entangled states are sensitive to magnetic fields, potentially allowing birds to visualize Earth's magnetic field lines. This quantum compass provides a precise navigation system that guides birds on their long-distance migrations. Enzyme catalysis, the process by which proteins accelerate chemical reactions in cells, appears to exploit quantum tunneling. In classical physics, chemical reactions require molecules to overcome an energy barrier. However, quantum tunneling allows particles to pass through these barriers rather than over them, greatly accelerating reaction rates. This quantum shortcut enables enzymes to catalyze reactions far more efficiently than classical physics would allow. The quantum nature of smell has emerged as another intriguing area of study. The traditional lock-and-key model of molecular recognition fails to explain how we can distinguish between molecules with identical shapes but different vibrational frequencies. Quantum mechanics suggests that electron tunneling in olfactory receptors might detect these molecular vibrations, enabling us to discriminate between similar molecules based on their quantum mechanical properties. Perhaps most provocatively, quantum mechanics might play a role in consciousness itself. The quantum nature of neural processes could help explain features of consciousness that seem difficult to account for with classical physics alone. Quantum coherence in microtubules within neurons, as proposed by the Penrose-Hameroff theory, might enable quantum computations that contribute to conscious experience. While controversial, these ideas suggest intriguing connections between quantum physics and mental processes. DNA, the molecule of heredity, may also exploit quantum effects. The stability of DNA-based pairs, crucial for maintaining genetic information, appears to involve quantum tunneling of protons between bases. This quantum dance helps explain how DNA can remain stable, yet flexible enough to be read and replicated. Furthermore, quantum effects might influence mutations, suggesting a quantum role in evolution itself. Biological quantum sensing extends beyond bird navigation. Some bacteria can detect quantum changes in Earth's magnetic field for orientation. Plants may use quantum mechanics to detect subtle variations in light quality during shade avoidance. Even human cells might employ quantum sensing mechanisms for various physiological processes, though many details remain to be discovered. The emerging field of quantum metabolism suggests that cellular energy production might involve quantum effects. The electron transport chain in mitochondria, which generates most of our cell's energy, could utilize quantum tunneling to move electrons more efficiently than classical physics would allow. This quantum efficiency might be crucial for maintaining life's high energy demands. The study of quantum biology raises fundamental questions about the role of quantum mechanics in evolution. Did life evolve to exploit quantum effects, or are quantum phenomena an inevitable consequence of life's molecular machinery? The persistence of quantum effects in warm, wet biological environments challenges our understanding of quantum decoherence and suggests that nature has found ways to protect and utilize quantum states. Quantum coherence in biological systems might extend beyond individual molecules to larger-scale structures. Recent evidence suggests that collections of atoms in biological molecules can maintain quantum coherence for surprisingly long times, potentially enabling quantum effects to influence macroscopic biological processes. This challenges the conventional wisdom that quantum effects are confined to the microscopic world. The implications of quantum biology extend to medical science and technology. Understanding how nature exploits quantum effects could lead to better solar cells inspired by photosynthesis, more efficient catalysts based on enzyme quantum tunneling, and new approaches to drug design that account for quantum effects in molecular interactions. Quantum biology might even suggest new therapeutic approaches based on manipulating biological quantum processes. The field also raises fascinating philosophical questions about the nature of life itself. If quantum effects are essential to fundamental biological processes, does this suggest a deeper connection between quantum mechanics and life? Could quantum phenomena be necessary for the emergence of life from non-living matter? These questions touch on the boundaries between physics, biology, and philosophy. As we develop more sophisticated tools for studying quantum effects in biological systems, we continue to discover new ways in which life harnesses quantum phenomena. From the molecular machinery of cells to the conscious experiences of organisms, quantum biology reveals nature's remarkable ability to operate at the boundary between quantum and classical realms. The study of quantum biology not only enhances our understanding of life, but also provides insights into quantum mechanics itself. Biological systems demonstrate how quantum effects can persist in complex, warm environments, challenging our assumptions about quantum decoherence and suggesting new approaches to quantum technology inspired by nature's solutions. The practical applications of quantum mechanics have revolutionized modern technology, leading to innovations that would seem like science fiction just decades ago. From quantum computers to ultra-precise atomic clocks, from quantum cryptography to quantum sensors, these technologies harness the strange properties of quantum mechanics to achieve capabilities far beyond classical devices. Quantum computing represents perhaps the most dramatic application of quantum principles. Unlike classical computers that process bits in definite states of 0 or 1, quantum computers use qubits that can exist in superpositions of states. This parallel processing capability allows quantum computers to solve certain problems exponentially faster than classical computers. For instance, factoring large numbers, a task crucial for cryptography, becomes dramatically more efficient on a quantum computer. The development of quantum computers faces significant technical challenges. Maintaining quantum coherence, keeping qubits in their delicate superposition states, requires extreme conditions, typically near absolute zero temperature. Various approaches compete to create stable qubits, from superconducting circuits to trapped ions, each with its own advantages and challenges. Error correction represents another crucial challenge, as quantum states are inherently fragile and susceptible to noise. Quantum sensing exploits quantum effects to achieve unprecedented measurement precision. Atomic clocks based on quantum transitions now keep time so accurately they would lose less than a second over billions of years. These ultra-precise timepieces enable GPS navigation and synchronize global telecommunications networks. Quantum sensors can also detect tiny changes in gravity, magnetic fields, and other physical quantities, with applications ranging from mineral exploration to medical imaging. Quantum cryptography offers the promise of unbreakable encryption based on fundamental quantum principles. The no-cloning theorem of quantum mechanics ensures that any attempt to intercept quantum encrypted communications necessarily disturbs the quantum states in a detectable way. Quantum key distribution systems, already commercially available, use this principle to generate secure encryption keys. As quantum computers threaten to break classical encryption methods, quantum cryptography becomes increasingly important for future cybersecurity. The quantum internet represents the next frontier in telecommunications. By transmitting quantum states between distant locations, a quantum network could enable secure communication, distributed quantum computing, and enhanced sensing capabilities. While significant technical challenges remain, prototype quantum networks are already being developed, with China launching the world's first quantum communications satellite in 2016. Quantum materials designed to exploit quantum effects show promise for various applications. Superconductors, which conduct electricity with zero resistance through quantum effects, could revolutionize power transmission and enable new types of electronic devices. Topological materials, whose electronic properties are protected by quantum mechanics, might form the basis for more robust quantum computers. The development of quantum metrology has enabled new standards for physical measurements. The kilogram, for instance, was recently redefined in terms of quantum mechanical properties rather than a physical artifact. Quantum voltage standards based on the Josephson effect provide ultra-precise electrical measurements. These quantum-based standards ensure consistent measurements worldwide and enable more precise scientific experiments. Quantum imaging techniques exploit quantum correlations to achieve resolution beyond classical limits. Ghost imaging uses quantum entangled photons to create images of objects without directly detecting the photons that interact with them. Quantum illumination can detect objects in noisy environments with unprecedented sensitivity. These techniques show promise for medical imaging, remote sensing, and security applications. The field of quantum simulation uses controlled quantum systems to study complex quantum phenomena. By creating artificial quantum systems in laboratories, scientists can investigate phenomena difficult to study in their natural context, from high-temperature superconductivity to early universe physics. These quantum simulators serve as powerful tools for both fundamental research and practical applications. Quantum-enhanced measurement devices exploit quantum effects to achieve greater precision than classical instruments. Quantum magnetometers can detect tiny magnetic fields with unprecedented sensitivity. Quantum gyroscopes could provide more accurate navigation systems. These devices find applications in geology, medicine, and navigation. The development of quantum technology has spurred advances in supporting technologies. Cryogenic systems for cooling quantum devices, precise laser systems for controlling quantum states, and sophisticated control electronics have all improved through quantum technology development. These advances benefit other fields beyond quantum applications. Quantum technology also impacts fields seemingly far from physics. Quantum-inspired algorithms improve classical computing methods. Quantum finance explores how quantum computing might transform financial modeling and optimization. Quantum machine learning investigates how quantum systems might enhance artificial intelligence. The commercialization of quantum technology has begun, with startups and major corporations investing in quantum computing, sensing, and cryptography. While many applications remain in early stages, the quantum technology industry grows rapidly. Government initiatives worldwide fund quantum technology development, recognizing its strategic importance. As quantum technologies mature, they increasingly interface with classical systems. Hybrid quantum classical computing combines quantum and classical processors to leverage the strengths of each. Quantum sensors integrate with classical electronics and data processing. This hybridization enables practical applications while more advanced quantum technologies develop. Understanding the limitations of quantum technology remains crucial. While quantum computers excel at specific tasks, they won't replace classical computers for most applications. Quantum effects remain fragile and difficult to maintain. Managing expectations while pursuing quantum advantages drives realistic technology development. The societal implications of quantum technology extend beyond technical capabilities. Quantum computing could break current encryption methods, requiring new cybersecurity approaches. Quantum sensing raises privacy concerns. These challenges require careful consideration of ethical and policy implications alongside technical development. The future of quantum technology holds immense promise while demanding continued innovation. As we develop better methods for controlling quantum systems, new applications will emerge. The challenge lies in bridging the gap between quantum principles and practical devices while managing technical challenges and societal implications. The interpretation of quantum mechanics remains one of physics' most profound and contentious issues. Beyond the mathematical formalism that makes such precise predictions lies the deeper question of what quantum mechanics tells us about the nature of reality itself. Different interpretations agree on experimental predictions, but offer radically different views of the underlying reality. The Copenhagen interpretation, long considered the standard view, suggests that quantum systems exist in superposition states until measured, at which point they collapse into definite states. This interpretation emphasizes the fundamental role of measurement in quantum mechanics, suggesting that unmeasured quantities don't have definite values. While pragmatically successful, it raises deep questions about the nature of measurement and consciousness's role in quantum mechanics. Hugh Everett's many worlds interpretation offers a more radical perspective. It proposes that when quantum measurements occur, reality splits into multiple branches, each representing a different possible outcome. Rather than wave functions collapsing, all possibilities actually occur in different, equally real universes. While mathematically elegant, this interpretation suggests an ever-branching reality of parallel worlds, challenging our intuitive sense of a single, definite reality. The pilot wave theory, developed by Louis de Broglie and David Bohm, maintains that particles always have definite positions, guided by an actual wave function. This interpretation preserves determinism and realism, but requires instantaneous action at a distance and an infinite number of hidden variables. While avoiding the measurement problem, it introduces other conceptual challenges about the nature of the guiding wave and its interaction with particles. Quantum Bayesianism, or cubism, takes a more epistemic approach, viewing quantum states as representations of knowledge rather than physical reality. In this interpretation, quantum mechanics describes our information about systems rather than the systems themselves. This view resolves many paradoxes, but raises questions about the relationship between knowledge and physical reality. The consistent histories interpretation attempts to resolve quantum paradoxes by focusing on consistent sequences of events rather than instantaneous states. It suggests that quantum mechanics only makes sense when considering complete histories of quantum systems, avoiding the need for collapse or multiple worlds. This approach provides a different perspective on quantum mechanics' temporal aspects. Decoherence theory, while not a complete interpretation, explains how quantum systems lose their quantum properties through interaction with their environment. This process helps bridge the quantum and classical worlds, showing how quantum superpositions effectively become classical states through environmental interaction. Understanding decoherence has practical implications for quantum technology development. The question of quantum reality connects to deeper philosophical issues about consciousness and free will. If consciousness plays a role in quantum measurement, as some interpretations suggest, what does this imply about the nature of consciousness itself? The relationship between quantum indeterminacy and human free will remains a topic of philosophical debate. Recent experimental tests have begun probing the boundaries between different quantum interpretations. While no experiment can definitively prove one interpretation correct, new tests of quantum contextuality, temporal correlations, and macroscopic superpositions provide insights into the quantum classical boundary and the nature of quantum reality. The role of time in quantum mechanics raises particularly puzzling questions. Different interpretations treat temporal evolution differently, from the reversible Schrödinger equation to irreversible collapse processes. Some approaches suggest that time itself might emerge from more fundamental quantum phenomena, challenging our basic understanding of temporal sequence. Quantum entanglement's implications for locality and causality continue to generate debate. Einstein's spooky action at a distance seems to violate special relativity's prohibition on faster-than-light influences, yet experiments consistently confirm quantum mechanics predictions. Different interpretations offer various resolutions to this apparent conflict between quantum mechanics and relativity. The measurement problem remains central to interpretational debates. What constitutes a measurement? When and how do quantum superpositions become definite outcomes? The various interpretations offer different answers, from consciousness-induced collapse to universal branching to fundamental uncertainty about unmeasured quantities. Information's role in quantum mechanics has gained increasing attention. Some approaches suggest that information might be more fundamental than matter or energy, with quantum mechanics describing information flow rather than physical objects. This perspective connects to broader questions about the nature of physical reality and its relationship to information. The emergence of classicality from quantum mechanics represents another crucial interpretational issue. How and why do we experience a seemingly classical world when fundamental reality is quantum mechanical? Different interpretations propose various mechanisms for this quantum to classical transition, from decoherence to consciousness-induced collapse. The relationship between quantum mechanics and space-time structure raises fundamental questions about reality's nature. Some approaches suggest that space-time itself might emerge from more fundamental quantum phenomena, while others propose modifications to quantum mechanics to better accommodate gravitational effects. These interpretational issues aren't merely philosophical. They guide research directions and technological development. Different interpretations suggest different approaches to quantum computing, quantum cryptography, and other practical applications. Understanding the relationship between quantum formalism and physical reality helps guide experimental design and technological innovation. As quantum technology advances, interpretational questions become increasingly practical. Building quantum computers requires understanding decoherence and measurement. Developing quantum cryptography systems needs clear concepts of quantum information and measurement. The interplay between theoretical interpretation and practical application continues driving progress in both areas. The search for a fully satisfying interpretation of quantum mechanics continues, with new proposals and refinements emerging regularly. While the mathematical formalism remains universally accepted, the quest to understand what it tells us about reality's fundamental nature drives ongoing research and philosophical discussion. The intersection of quantum mechanics and chaos theory reveals fascinating insights about complexity in the quantum realm. While classical chaos theory deals with systems whose behavior becomes unpredictable due to extreme sensitivity to initial conditions, quantum chaos explores how quantum systems exhibit complex behavior despite their fundamentally probabilistic nature. Classical chaos appears in familiar systems like weather patterns, where tiny changes in initial conditions can lead to dramatically different outcomes, the famous butterfly effect. However, quantum mechanics' uncertainty principle makes it impossible to specify exact initial conditions, raising the question of how chaos manifests in quantum systems. This fundamental difference between classical and quantum mechanics leads to unique features in quantum chaotic systems. Consider a simple quantum system like an atom in a strong magnetic field. Classical physics would predict chaotic behavior as the electron's orbit becomes increasingly complex. In the quantum realm, however, the electron's wave function evolves according to strict quantum mechanical rules. The resulting behavior shows signatures of chaos while maintaining quantum coherence, a phenomenon known as quantum chaos. The quantum suppression of chaos represents one striking difference between classical and quantum systems. While classical chaotic systems show exponential sensitivity to initial conditions, quantum systems can exhibit the same degree of chaos due to the uncertainty principle. This quantum freeze of chaos leads to interesting phenomena, like quantum scars, unexpected regularities in otherwise chaotic quantum systems. Quantum scarring occurs when quantum wave functions show enhanced intensity along unstable periodic orbits of the corresponding classical system. These scars represent a kind of quantum memory of classical periodic motion, persisting even in systems that would be completely chaotic classically. This phenomenon has practical implications for quantum control and quantum computing, as quantum scars might help preserve quantum information in otherwise chaotic systems. The study of quantum chaos connects to fundamental questions about quantum classical correspondence. As quantum systems become larger and more complex, they're expected to exhibit behavior increasingly similar to classical systems, a principle known as the correspondence principle. However, quantum chaos shows that this transition isn't straightforward, with quantum effects persisting in unexpected ways, even in complex systems. Quantum signatures of chaos appear in various physical systems, from atomic nuclei to quantum dots to light waves in optical cavities. These signatures include statistical properties of energy levels, wave function patterns, and dynamic behavior that differ systematically from non-chaotic quantum systems. Understanding these signatures helps scientists identify and characterize quantum chaotic systems. The relationship between quantum chaos and entanglement provides another fascinating area of study. Chaotic quantum systems tend to generate entanglement more efficiently than non-chaotic ones, potentially making them useful for quantum information processing. This connection between chaos and entanglement suggests deep links between quantum complexity and quantum information. Quantum chaos also plays a role in understanding thermalization, how isolated quantum systems approach thermal equilibrium. Chaotic quantum systems typically thermalize more efficiently than non-chaotic ones, following a process called eigenstate thermalization. This phenomenon helps explain how macroscopic systems reach equilibrium despite following quantum mechanical laws. The study of quantum chaos extends to many-body systems, where multiple particles interact quantum mechanically. These systems can exhibit particularly rich behavior, with complex patterns of entanglement and correlation emerging from simple, underlying interactions. Many-body quantum chaos plays a crucial role in understanding phenomena from nuclear reactions to quantum computing. Recent experiments have begun probing quantum chaos directly, using technologies like ultra-cold atoms and superconducting circuits. These systems allow scientists to control and measure quantum behavior with unprecedented precision, providing new insights into how chaos manifests in the quantum realm. Such experiments help bridge the gap between theoretical predictions and observable phenomena. The implications of quantum chaos extend to cosmology and black hole physics. The chaotic nature of quantum fields near black hole horizons connects to questions about information preservation and the black hole information paradox. Some theories suggest that quantum chaos might play a crucial role in resolving these paradoxes through complex patterns of entanglement. Understanding quantum chaos has practical applications in quantum technology. Quantum devices must often operate in regimes where chaos becomes important, making it crucial to understand how quantum chaos affects their performance. This knowledge helps in designing more robust quantum computers and quantum communication systems. The field of quantum control aims to manipulate quantum systems, despite their chaotic tendencies. Techniques like optimal control theory and feedback control can help maintain quantum coherence even in chaotic systems. These methods are essential for practical quantum computing and other quantum technologies. Quantum chaos also influences our understanding of quantum measurement. The sensitivity of chaotic systems to measurement makes them particularly interesting for studying the quantum measurement problem. Some theories suggest that chaos might play a role in the emergence of classical behavior from quantum systems through the measurement process. The relationship between quantum chaos and complexity theory raises deeper questions about the nature of complexity in quantum systems. While classical complexity theory deals with computational resources needed to solve problems, quantum complexity must account for uniquely quantum resources like entanglement and superposition. As we develop more sophisticated tools for studying quantum systems, our understanding of quantum chaos continues to evolve. New experimental techniques and theoretical frameworks reveal increasingly subtle aspects of how chaos manifests in the quantum realm. This understanding helps bridge the gap between quantum and classical physics, while revealing unique quantum phenomena with no classical counterpart. The study of quantum chaos reminds us that even in a fundamentally probabilistic theory like quantum mechanics, complex and seemingly unpredictable behavior can emerge from simple rules. Understanding this complexity helps us better grasp both the fundamental nature of quantum systems and their practical applications in modern technology. The quantum vacuum, far from being empty nothingness, teems with activity at the microscopic level. Quantum field theory reveals that what we perceive as empty space is actually filled with quantum fields in their lowest energy states, constantly fluctuating and producing virtual particles that pop in and out of existence. This quantum foam forms the foundation of our understanding of particle physics and the nature of vacuum itself. In quantum field theory, every type of particle is associated with an underlying field that permeates all of space. Even in their ground states, these fields exhibit zero-point energy, an irreducible amount of energy that cannot be removed due to the uncertainty principle. These vacuum fluctuations lead to measurable effects, such as the Casimir force between closely spaced metal plates, where quantum fluctuations create a tiny but detectable attractive force. Virtual particles emerge from these vacuum fluctuations, appearing in pairs that quickly annihilate each other in accordance with Heisenberg's uncertainty principle. These particle-antiparticle pairs can briefly violate energy conservation, borrowing energy from the vacuum for extremely short periods. While these virtual particles cannot be directly observed, their effects manifest in various measurable phenomena. The vacuum state plays a crucial role in particle physics experiments. When particles collide with sufficient energy, they can excite the quantum vacuum, creating real particles from these vacuum fluctuations. This process underlies particle creation in accelerators, like the Large Hadron Collider, where vacuum fluctuations materialize into observable particles when supplied with enough energy. Quantum electrodynamics, QED, provides our most precise description of how charged particles interact through the electromagnetic field. The vacuum fluctuations in QED modify the properties of particles in subtle but measurable ways. For example, the electron's magnetic moment differs slightly from what simpler theories predict due to its interaction with virtual particles in the vacuum, a difference that has been measured with extraordinary precision. The Higgs field represents a special kind of quantum field whose vacuum state has profound consequences for particle physics. Unlike other quantum fields, the Higgs field has a non-zero vacuum expectation value, creating what physicists call a vacuum condensate. This symmetry-breaking vacuum state gives mass to other particles through their interactions with the Higgs field. Vacuum polarization occurs when virtual particle-antiparticle pairs temporarily screen electric charges. This effect makes the apparent strength of the electromagnetic force depend on distance, becoming stronger at shorter distances, where the screening becomes less effective. Similar screening effects occur in other quantum fields, affecting how forces behave at different energy scales. The quantum vacuum may also play a crucial role in cosmology. Vacuum energy could contribute to the cosmological constant, potentially driving the accelerated expansion of the universe. However, theoretical predictions for vacuum energy density differ from observed values by many orders of magnitude. The cosmological constant problem remains one of physics' greatest unsolved puzzles. Modern theories suggest that the vacuum state might not be unique. String theory predicts an enormous landscape of possible vacuum states, each corresponding to a universe with different physical constants and laws. This vacuum landscape could provide a framework for understanding the apparent fine-tuning of our universe's parameters through anthropic selection. Quantum phase transitions can occur when the vacuum state of a quantum field changes character. These transitions, different from ordinary phase transitions driven by temperature, can lead to dramatic changes in a system's properties, even at absolute zero temperature. Understanding these quantum phase transitions provides insights into exotic states of matter and possible early universe physics. The concept of false vacuum decay raises intriguing possibilities about the stability of our universe. If our current vacuum state is metastable, it could potentially tunnel to a lower energy state through quantum processes, fundamentally altering the laws of physics in affected regions. While such an event seems unlikely, the possibility illustrates the dynamic nature of the quantum vacuum. Vacuum states in curved space-time exhibit particularly interesting properties. Near black holes, the vacuum becomes distorted, leading to phenomena like Hawking radiation, where the curved space-time creates real particles from vacuum fluctuations. This connection between gravity and quantum fields provides crucial insights for theories of quantum gravity. The study of quantum vacuum effects has practical applications in modern technology. Understanding how materials modify the vacuum state leads to better designs for quantum devices. Vacuum engineering might eventually allow us to manipulate vacuum fluctuations for technological purposes, from improving quantum computers to designing new types of sensors. Recent experimental advances have allowed direct observation of vacuum fluctuation effects. Using techniques like ultra-fast laser pulses, scientists can probe the quantum vacuum and observe its influence on light propagation. These experiments provide crucial tests of quantum field theory while suggesting new ways to harness vacuum effects. The quantum vacuum's properties continue to surprise physicists, revealing new phenomena and challenging our understanding of empty space. As we develop better theoretical tools and experimental techniques, we may discover even more remarkable features of the quantum vacuum, leading to new insights about the fundamental nature of reality and possible technological applications. The study of quantum vacuum states reminds us that emptiness itself has complex structure and dynamics at the quantum level. This understanding transforms our view of space from a passive backdrop to an active participant in physical processes, fundamentally shaping how particles and forces behave in our universe. The quantum nature of light reveals some of the most striking demonstrations of quantum mechanics in action. When we study light at its most fundamental level, we find that it exhibits both wave-like and particle-like properties, a duality that challenges our classical intuitions but opens up remarkable possibilities for technology and understanding nature. Photons, the quantum particles of light, serve as ideal quantum systems for study and manipulation. Unlike massive particles, photons can maintain quantum coherence over long distances and are relatively easy to create and detect. This makes them perfect tools for exploring quantum phenomena and developing quantum technologies. Each photon carries a discrete packet of energy determined by its frequency, demonstrating the quantization that gives quantum mechanics its name. The interaction between light and matter at the quantum level shows extraordinary subtlety and complexity. When atoms absorb or emit photons, they transition between discrete energy levels in ways that can only be explained through quantum mechanics. These quantum jumps between energy states occur instantaneously, without passing through intermediate states, demonstrating the fundamentally discrete nature of quantum processes. Quantum optics reveals phenomena with no classical analogs. Consider quantum superposition in optical systems. A single photon can simultaneously take multiple paths through an interferometer, interfering with itself in ways impossible for classical particles. This quantum behavior enables technologies like quantum cryptography, where the quantum nature of photons ensures secure communication. The creation of entangled photons represents another triumph of quantum optics. Through processes like spontaneous parametric down conversion, scientists can create pairs of photons whose quantum states are inextricably linked, regardless of their separation distance. These entangled photons serve as resources for quantum information processing and tests of quantum mechanics' fundamental principles. Cavity quantum electrodynamics studies the interaction between atoms and photons confined in optical cavities. When atoms interact with the quantized electromagnetic field in a cavity, they can exhibit striking quantum effects like vacuum-Rabi oscillations, where energy coherently transfers between the atom and the cavity field. These systems provide controlled environments for studying quantum phenomena and developing quantum technologies. The quantum nature of light enables new types of measurement and imaging. Quantum microscopy uses entangled photons to achieve resolution beyond classical limits. Ghost imaging exploits quantum correlations to create images without directly detecting the photons that interact with the object. These techniques push the boundaries of what's possible in optical measurement and imaging. Squeezed light represents another uniquely quantum phenomenon. By manipulating quantum uncertainties, scientists can reduce noise in one measurement variable at the expense of increased noise in another, following the uncertainty principle. This quantum squeezing finds applications in gravitational wave detection and precision measurement. The development of single photon sources and detectors has revolutionized quantum optics. Creating reliable sources of individual photons and detecting them with high efficiency enables new experiments and technologies. These capabilities form the backbone of optical quantum computing and quantum communication systems. Quantum memories for light allow the storage and retrieval of quantum states, essential for quantum networks and quantum computing. These memories must preserve the quantum coherence of stored states while allowing controlled retrieval. Various approaches use atomic ensembles, crystal defects, or other quantum systems to achieve this storage. The interaction between light and mechanical systems at the quantum level reveals fascinating phenomena. Optomechanical systems, where light interacts with mechanical resonators, can reach regimes where quantum effects dominate. These systems enable the study of quantum behavior in relatively large objects and have applications in quantum sensing. Quantum nonlinear optics studies how light behaves in materials at the quantum level. When individual photons interact with materials, they can exhibit nonlinear effects that differ from classical behavior. These quantum nonlinearities enable the creation of photonic quantum gates and other devices essential for quantum information processing. The development of quantum light sources has enabled new types of spectroscopy and sensing. Sources of squeezed light, entangled photons, and other non-classical states provide new tools for probing matter and measuring physical quantities with unprecedented precision. These quantum-enhanced measurements push the boundaries of what we can observe and measure. The quantum theory of laser operation reveals deeper insights about light-matter interaction. While lasers can be partially understood through classical physics, their full description requires quantum mechanics. Quantum effects determine fundamental laser properties like line width and coherence, and enable new types of quantum light sources. Quantum optics also provides tools for studying fundamental physics. Optical atomic clocks use quantum transitions in atoms to achieve incredible precision in timekeeping. These clocks enable tests of fundamental physics theories and have practical applications in navigation and communication. The field continues to advance with new theoretical proposals and experimental techniques. Topological photonics studies how topology affects quantum optical systems. Quantum metamaterials engineer optical properties at the quantum level. These developing areas promise new capabilities for controlling and utilizing quantum light. Understanding quantum optics has profound implications for our view of reality. The quantum nature of light challenges classical intuitions about locality and causality, while opening new technological possibilities. As we develop better ways to control and measure quantum light, we gain deeper insights into the quantum nature of reality itself. Preparing and narrating this theory took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the theory. The quantum behavior of matter near absolute zero temperature reveals extraordinary phenomena that challenge our understanding of phase transitions. Unlike classical phase transitions driven by thermal fluctuations, quantum phase transitions occur at zero temperature and are driven by quantum fluctuations arising from Heisenberg's uncertainty principle. These transitions reveal deep connections between quantum mechanics and the emergence of collective behavior in many body systems. Quantum phase transitions occur when varying a physical parameter like magnetic field or pressure causes a dramatic change in a system's ground state. At the critical point of such a transition, the system exhibits unique properties that emerge from quantum correlations spanning all length scales. This quantum critical behavior differs fundamentally from classical critical phenomena, showing unique scaling laws and universality classes. Consider a system of quantum spins in a magnetic field. As the field strength changes, the spins might suddenly reorient themselves, marking a quantum phase transition. Unlike classical magnetic transitions driven by temperature, this reorientation happens even at absolute zero, purely due to quantum effects. The system's wave function undergoes a fundamental reorganization, often accompanied by the emergence of long-range quantum entanglement. The study of quantum phase transitions reveals how quantum mechanics influences collective behavior in many particle systems. Near a quantum critical point, the system's properties show universal behavior independent of microscopic details. This universality, similar to that seen in classical phase transitions, but with distinct quantum characteristics, helps us understand how complex behavior emerges from quantum systems. Quantum criticality often leads to exotic states of matter. Examples include quantum spin liquids, where magnetic moments refuse to order even at zero temperature due to quantum fluctuations, and topological phases, where the system's properties depend on global rather than local features. These states have no classical analogs and represent uniquely quantum forms of matter. The role of entanglement in quantum phase transitions provides crucial insights into quantum many-body physics. Near a quantum critical point, entanglement entropy often shows distinctive scaling behavior, reflecting the system's quantum correlations. This connection between entanglement and criticality helps us understand how quantum information spreads through many body systems. Experimental studies of quantum phase transitions require extreme conditions, typically ultra-low temperatures and precise control over system parameters. Cold atom systems provide ideal platforms for studying these transitions, allowing researchers to tune interactions and observe quantum critical behavior directly. Quantum simulators, built from arrays of trapped atoms or superconducting circuits, enable detailed investigation of quantum critical phenomena. The dynamics near quantum critical points show remarkable features. When a system is driven across a quantum phase transition, It cannot respond instantaneously due to fundamental quantum mechanical limitations. This leads to universal behavior in how defects form, described by the Kibble-Zurich mechanism. Understanding these dynamics has practical implications for adiabatic quantum computation and quantum annealing. Quantum phase transitions also influence finite temperature properties of materials. Even when thermal fluctuations dominate, proximity to a quantum critical point can dramatically affect a system's behavior, leading to unusual temperature dependence of various physical properties. This quantum critical fan extends the influence of quantum criticality to experimentally accessible temperatures. The interplay between quantum and thermal fluctuations near quantum critical points creates rich phase diagrams. Systems might exhibit multiple competing phases with complex transitions between them. Understanding this competition helps explain phenomena like high-temperature superconductivity, where quantum critical fluctuations might play a crucial role. Mathematical tools for studying quantum phase transitions draw from both quantum mechanics and statistical physics. Quantum field theory provides a framework for describing critical behavior, while numerical methods like quantum Monte Carlo simulation help explore systems too complex for analytical treatment. These approaches reveal universal features of quantum criticality. The concept of quantum phase transitions extends beyond condensed matter physics. Similar phenomena appear in quantum optical systems, nuclear physics, and even quantum cosmology. The universal aspects of quantum criticality suggest deep connections between seemingly different physical systems sharing similar symmetries and dimensionality. Applications of quantum critical phenomena include quantum sensing and quantum computation. Systems near quantum critical points often show enhanced sensitivity to external perturbations, making them useful for detecting weak signals. Quantum annealing exploits quantum critical behavior for optimization problems, offering potential advantages over classical algorithms. Recent research explores connections between quantum criticality and quantum information concepts. The growth of entanglement near critical points relates to quantum circuit complexity and holographic descriptions of quantum systems. These connections suggest deeper relationships between quantum criticality and fundamental aspects of quantum information processing. Understanding quantum phase transitions has practical implications for quantum device design. Devices operating near quantum critical points might exhibit enhanced functionality, but also increased sensitivity to noise and perturbations. Balancing these effects requires careful consideration of quantum critical behavior in device engineering. The study of quantum phase transitions continues to reveal new phenomena and challenge our understanding of quantum many-body physics. As experimental capabilities advance and theoretical tools develop, we gain deeper insights into how quantum mechanics shapes collective behavior at the most fundamental level. This understanding may lead to new technological applications while illuminating basic questions about the emergence of complexity in quantum systems. The preservation of quantum information against errors and decoherence represents one of the greatest challenges in quantum computing and quantum information processing. Unlike classical information, quantum states are inherently fragile, easily disturbed by interaction with their environment. Quantum error correction provides a framework for protecting quantum information. making reliable quantum computation possible despite the presence of noise and errors. The fundamental challenge of quantum error correction stems from the quantum no-cloning theorem, which states that arbitrary quantum states cannot be perfectly copied. This limitation means we cannot simply make backup copies of quantum information as we do with classical data. Instead, quantum error correction employs sophisticated encoding schemes that spread quantum information across multiple physical qubits to create protected logical qubits. The simplest quantum error correcting codes protect against single qubit errors by encoding one logical qubit into several physical qubits. For example, the 3-qubit bit flip code encodes quantum information across 3 physical qubits in a way that allows detection and correction of single-bit flip errors. More sophisticated codes can protect against multiple types of errors simultaneously, crucial for practical quantum computation. Surface codes represent a particularly promising approach to quantum error correction. These codes arrange physical qubits in a 2-dimensional lattice, with error correction properties emerging from the topology of the lattice. Surface codes are relatively tolerant of errors in their implementation and require only local interactions between nearby qubits, making them practically feasible with current technology. The threshold theorem for quantum computation provides a crucial theoretical foundation for quantum error correction. This theorem states that if the error rate per physical operation can be reduced below a certain threshold, arbitrarily long quantum computations become possible through error correction. This result gives hope that practical quantum computers are possible despite the inherent fragility of quantum states. Fault-tolerant quantum computation extends error correction principles to entire quantum circuits. Not only must the quantum information be protected, but the operations performed on it must also be implemented in ways that prevent errors from propagating uncontrollably. Fault-tolerant protocols ensure that small errors remain localized and can be corrected before they spread throughout the computation. The implementation of quantum error correction requires careful consideration of resource trade-offs. Protecting quantum information requires significant overhead in terms of additional physical qubits and quantum gates. Current estimates suggest that thousands of physical qubits might be needed for each logical qubit in a fault-tolerant quantum computer. Optimizing this overhead while maintaining reliable operation remains an active area of research. Continuous variable quantum error correction addresses the protection of quantum systems with continuous degrees of freedom, such as the position and momentum of mechanical oscillators or the amplitude and phase of electromagnetic fields. These systems present unique challenges and opportunities for error correction, requiring different approaches than discrete qubit-based systems. The development of hardware-efficient error correction schemes represents a crucial step toward practical quantum computers. Different physical implementations of quantum bits have different types of dominant errors and different capabilities for measurement and control. Error correction schemes must be adapted to take advantage of the strengths and mitigate the weaknesses of specific hardware platforms. Quantum feedback control provides another approach to error suppression, complementing traditional error correction codes. By continuously monitoring quantum systems and applying corrective operations based on measurement results, feedback control can help maintain quantum states and improve the fidelity of quantum operations. The integration of feedback control with error correction codes offers promising possibilities for robust quantum systems. The connection between quantum error correction and fundamental physics reveals deeper insights about quantum information. Error-correcting codes naturally emerge in certain physical systems, suggesting connections between quantum protection mechanisms in nature and engineered quantum error correction. These connections might help us understand both practical quantum computing and fundamental quantum mechanics. Recent developments in machine learning have begun to impact quantum error correction. Neural networks and other machine learning techniques can help optimize error correction protocols and decode error syndromes more efficiently. These approaches might lead to more effective error correction strategies as quantum systems grow in complexity. The experimental implementation of quantum error correction continues to advance. Small-scale demonstrations have shown the basic principles work in practice, while larger implementations face ongoing technical challenges. Success in scaling up these demonstrations will be crucial for realizing practical quantum computers. The relationship between quantum error correction and quantum memory highlights important connections in quantum information science. Long-term storage of quantum information requires effective error correction, while the implementation of error correction requires at least short-term quantum memory. Understanding this interplay helps in designing better quantum information systems. The future of quantum error correction will likely involve hybrid approaches, combining different protection mechanisms. Traditional error-correcting codes might work alongside dynamical decoupling techniques, feedback control, and hardware-specific optimizations. This multi-layered approach to quantum protection might offer the best path toward reliable quantum computation. The challenge of quantum error correction exemplifies both the difficulties and opportunities in quantum information science. While protecting quantum information is fundamentally harder than protecting classical information, the development of error correction techniques has deepened our understanding of quantum mechanics and opened new possibilities for quantum technology. The act of measurement in quantum mechanics represents one of its most profound and mysterious aspects. Unlike classical systems, where measurement simply reveals pre-existing properties, quantum measurement fundamentally affects the system being measured, collapsing quantum superpositions into definite states. Understanding and controlling this measurement process is crucial for both fundamental physics and practical quantum technologies. Quantum measurement theory extends beyond the simple projection postulate of basic quantum mechanics. The theory of positive operator-valued measures, POVMs, provides a more general framework for describing quantum measurements, including weak measurements, continuous measurements, and partial measurements. This framework reveals subtle aspects of how information can be extracted from quantum systems. Weak measurements allow us to gather information about quantum systems without completely collapsing their quantum states. By making the interaction between the measurement apparatus and the quantum system sufficiently gentle, we can obtain partial information while preserving some quantum coherence. These techniques have revealed surprising features of quantum systems and enabled new experimental approaches to studying quantum phenomena. The quantum Zeno effect demonstrates how repeated measurements can influence quantum evolution. Frequent measurements of a quantum system can effectively freeze its evolution, preventing transitions between quantum states. Conversely, carefully designed sequences of measurements can guide quantum evolution in desired directions, providing tools for quantum control. Quantum feedback control combines measurement with dynamic control of quantum systems. By continuously monitoring a quantum system and adjusting control parameters based on measurement results, we can maintain desired quantum states or guide system evolution. This approach proves particularly valuable in quantum computing and precision measurement applications. The role of decoherence in quantum measurement highlights the connection between measurement and environmental interaction. Decoherence theory explains how interaction with the environment effectively performs continuous measurement of quantum systems, causing the transition from quantum to classical behavior. Understanding this process is crucial for protecting quantum information and designing quantum devices. Quantum non-demolition, QND, measurements represent a special class of measurements that can be repeated without disturbing certain properties of the quantum system. These measurements are particularly valuable for quantum sensing and monitoring applications, allowing continuous observation of quantum systems without completely disrupting their quantum states. The implementation of precise quantum measurements requires sophisticated experimental techniques. Quantum limited amplifiers, single photon detectors, and other advanced measurement tools push the boundaries of what can be observed in quantum systems. The development of these techniques continues to enable new experiments and applications in quantum science. Entanglement-enhanced measurement schemes exploit quantum correlations to achieve precision beyond classical limits. Quantum metrology uses entangled states to improve measurement sensitivity, approaching the fundamental Heisenberg limit. These techniques find applications in atomic clocks, gravitational wave detection, and other precision measurements. The quantum measurement problem connects to fundamental questions about consciousness and reality. Various interpretations of quantum mechanics propose different views on what happens during measurement, from consciousness-induced collapse to the branching of multiple worlds. While these philosophical questions remain debated, practical approaches to quantum measurement continue to advance. Continuous measurement theory describes how quantum systems evolve under constant observation. The quantum trajectory approach provides a framework for understanding how individual quantum systems behave when continuously monitored, revealing new insights about quantum dynamics and measurement. The connection between measurement and thermodynamics reveals deep principles about information and energy. Landauer's principle relates the erasure of information to energy dissipation, while the role of measurement in Maxwell's demon thought experiment highlights fundamental connections between information and entropy. Quantum tomography provides techniques for completely characterizing quantum states through multiple measurements. This process requires careful design of measurement protocols and sophisticated data analysis to reconstruct quantum states from measurement results. Advances in quantum tomography enable better characterization and validation of quantum devices. The development of adaptive measurement schemes allows optimization of measurement strategies based on previous results. These techniques can improve measurement efficiency and precision by dynamically adjusting measurement parameters. Machine learning approaches increasingly contribute to optimizing these adaptive measurements. Quantum measurement plays a crucial role in quantum error correction. Syndrome measurements must detect errors without disturbing the encoded quantum information, requiring careful design of measurement protocols. The ability to perform fast, accurate measurements is essential for practical quantum error correction. The back action of quantum measurement on measured systems provides both challenges and opportunities. While measurement back action can disrupt quantum states, it can also be harnessed for quantum control and state preparation. Understanding and controlling measurement back action is crucial for many quantum applications. Quantum measurement also influences quantum communication protocols. Quantum key distribution relies on the inability to measure quantum states without disturbance, while quantum teleportation requires precise measurements to reconstruct quantum states. The properties of quantum measurement thus enable secure communication protocols. The development of quantum sensors pushes the boundaries of measurement precision. Quantum-enhanced sensing exploits quantum effects to achieve sensitivity beyond classical limits. Applications range from magnetic field detection to gravitational sensing, with potential impacts across science and technology. The relationship between measurement and quantum coherence reveals fundamental aspects of quantum systems. Understanding how measurement affects quantum coherence and how to preserve coherence during measurement remains crucial for quantum technology development. This understanding continues to evolve as we develop better theoretical tools and experimental techniques. The future of quantum measurement and control promises new capabilities in quantum technology, while deepening our understanding of quantum mechanics itself. As we develop more sophisticated measurement techniques and control strategies, we unlock new possibilities for quantum computing, sensing, and fundamental physics exploration. Quantum algorithms represent a fundamental departure from classical computing, exploiting quantum phenomena like superposition and entanglement to solve certain problems exponentially faster than classical computers. These algorithms operate on quantum bits, or qubits, which can exist in multiple states simultaneously, enabling parallel processing at a scale impossible for classical computers. Shor's algorithm stands as one of the most significant quantum algorithms, capable of factoring large numbers exponentially faster than the best-known classical algorithms. This capability has profound implications for cryptography, as many current encryption methods rely on the difficulty of factoring large numbers. The algorithm works by using quantum Fourier transforms to find periodic patterns in numerical sequences, demonstrating how quantum computers can exploit mathematical structure in ways classical computers cannot. Grover's algorithm provides another striking example of quantum advantage, offering quadratic speedup for unstructured search problems. While not as dramatic as Shor's exponential speedup, Grover's algorithm has broader applicability, potentially improving various optimization and search tasks. The algorithm uses quantum amplitude amplification to enhance the probability of finding desired solutions in a quantum superposition. Quantum phase estimation forms a crucial subroutine in many quantum algorithms, enabling precise measurement of quantum state phases. This technique underlies various quantum algorithms for simulation and optimization problems. The ability to estimate phases efficiently exemplifies how quantum computers can extract information encoded in quantum states. The quantum Fourier transform serves as a fundamental building block for many quantum algorithms, providing an exponentially faster version of the classical Fourier transform. This transformation enables efficient analysis of periodic structures in quantum data, crucial for applications ranging from factoring to quantum simulation. Quantum simulation algorithms represent a natural application of quantum computing, using controlled quantum systems to simulate other quantum systems. These algorithms could revolutionize materials, science, chemistry, and drug discovery by enabling accurate simulation of quantum mechanical processes beyond the reach of classical computers. Variational quantum algorithms offer a promising approach for near-term quantum computers with limited coherence times. These hybrid classical quantum algorithms use quantum systems for specific subroutines while leveraging classical computers for optimization. The quantum approximate optimization algorithm, QAOA, exemplifies this approach, targeting combinatorial optimization problems. Quantum machine learning algorithms combine quantum computing with machine learning techniques, potentially offering speed-ups for certain learning tasks. These algorithms exploit quantum linear algebra subroutines and quantum feature spaces to enhance classical machine learning approaches. The field continues to explore which aspects of machine learning can benefit from quantum advantage. Error mitigation strategies play crucial roles in implementing quantum algorithms on noisy intermediate-scale quantum NISQ devices. These techniques include error extrapolation, probabilistic error cancellation, and symmetry verification, enabling meaningful computation despite hardware limitations. The development of quantum circuits and gates provides the physical implementation of quantum algorithms. Universal quantum computation requires both single-qubit operations and entangling gates between qubits. The challenge lies in implementing these operations with sufficient fidelity while maintaining quantum coherence. Quantum algorithm complexity theory studies the computational resources required by quantum algorithms, developing frameworks for comparing quantum and classical computational power. This theoretical foundation helps identify which problems might benefit from quantum computation and establishes fundamental limits on quantum speedup. The concept of quantum supremacy represents the threshold where quantum computers perform tasks beyond classical capability. Demonstrating quantum supremacy requires carefully chosen problems that highlight quantum advantages while remaining verifiable by classical computers. Quantum error correction enables reliable quantum computation despite noise and decoherence. Fault-tolerant quantum computation requires encoding logical qubits across multiple physical qubits, with error correction protocols maintaining quantum information throughout computation. Quantum memory and quantum communication protocols complement quantum algorithms, enabling distributed quantum computation and long-term storage of quantum states. These capabilities prove essential for scaling quantum computation beyond single processor limitations. The development of quantum software frameworks facilitates quantum algorithm implementation and testing. These tools provide high-level abstractions for quantum programming while handling low-level optimization and error mitigation. The evolution of these frameworks continues alongside hardware development. Benchmarking quantum algorithms requires careful consideration of both quantum and classical performance metrics. Meaningful comparisons must account for different hardware capabilities and problem-specific requirements. The field continues developing standardized benchmarking approaches. Applications of quantum algorithms extend across various domains, from cryptography and optimization to materials science and financial modeling. Each application area presents unique challenges and opportunities for quantum advantage. Understanding which problems benefit from quantum computation remains an active research area. The connection between quantum algorithms and fundamental physics reveals deep insights about computation and physical reality. Quantum computation may provide new perspectives on quantum mechanics itself, while physical principles continue informing algorithm development. The practical implementation of quantum algorithms faces significant challenges, including decoherence, gate errors, and limited connectivity between qubits. Addressing these challenges requires advances in both hardware technology and algorithm design. The field continues evolving toward practical quantum computation. The future of quantum algorithms promises both theoretical insights and practical applications. As quantum hardware capabilities advance, new algorithms emerge to exploit these capabilities. The ongoing development of quantum algorithms drives progress toward practical quantum computation, while deepening our understanding of quantum information processing. Physical implementations of quantum computers face fundamental challenges in maintaining quantum coherence while enabling precise control and measurement of quantum states. Different approaches compete to create scalable quantum computing platforms, each with unique advantages and technical hurdles. Superconducting circuits represent a leading approach to quantum computing, using Josephson junctions to create artificial atoms that serve as qubits. These systems operate at millikelvin temperatures to maintain quantum coherence, using microwave pulses for control and readout. The technology enables strong coupling between qubits and fast gate operations, though maintaining coherence remains challenging. Trapped ion systems use individual atomic ions held in electromagnetic fields as qubits. These systems offer exceptional coherence times and high-fidelity operations, with ions manipulated using laser pulses. The challenge lies in scaling to larger numbers of qubits while maintaining precise control over ion positions and interactions. Quantum dots in semiconductors provide another platform for quantum computation, using electron spins or charge states as qubits. These solid-state devices integrate well with existing semiconductor technology, but face challenges in maintaining coherence and achieving uniform properties across multiple qubits. Photonic quantum computing uses individual photons as qubits, exploiting their natural ability to maintain coherence over long distances. Linear optical quantum computing requires precise control over photon creation, manipulation, and detection. The challenge lies in creating deterministic photon-photon interactions necessary for universal quantum computation. Neutral atom arrays use individual atoms trapped in optical lattices or tweezer arrays as qubits. These systems offer natural scalability and uniformity, with atoms manipulated using laser pulses. Recent advances in Rydberg atom interactions enable strong coupling between qubits, though maintaining precise control remains challenging. Diamond nitrogen vacancy centers provide optically accessible spin qubits operating at room temperature. These solid-state defects offer long coherence times and natural coupling to photons, enabling quantum networking applications. Scaling to larger systems while maintaining precise control presents ongoing challenges. Topological quantum computing proposes using exotic quantum states of matter to create inherently error-protected qubits. While theoretically promising, demonstrating topological qubits remains an experimental challenge. Success could revolutionize quantum computing by drastically reducing error correction overhead. Hybrid approaches combine different quantum systems to leverage their complementary strengths. For example, systems might use superconducting circuits for processing while employing photons for communication between quantum processors. These hybrid architectures could enable distributed quantum computing networks. Control systems for quantum computers require precise timing and minimal noise. Classical electronics must generate and shape control pulses while filtering noise that could disrupt quantum coherence. Developing robust control systems remains crucial for scaling quantum computers. Quantum error correction implementation demands high-fidelity measurement and feedback control. Physical qubits must be measured and corrected faster than error rates to maintain quantum information. Achieving these requirements while scaling to larger systems poses significant engineering challenges. Cryogenic systems play crucial roles in many quantum computing platforms. Maintaining stable, ultra-low temperatures while allowing for control and measurement access requires sophisticated engineering. Scaling cryogenic systems for larger quantum processors presents ongoing challenges. Quantum classical interfaces enable communication between quantum processors and classical computers. These interfaces must efficiently transfer control signals and measurement results while minimizing noise and maintaining quantum coherence. Developing effective interfaces remains important for practical quantum computing. Fabrication techniques for quantum devices require exceptional precision and uniformity. Small variations in device parameters can significantly impact qubit performance. Developing reliable, scalable fabrication processes remains crucial for quantum computer manufacturing. Integration challenges arise when combining different components into complete quantum computing systems. Maintaining quantum coherence while providing necessary control and measurement capabilities requires careful system design. Addressing these integration challenges remains important for practical quantum computers. Material properties fundamentally affect quantum device performance. Understanding and controlling material defects, interfaces, and noise sources remains crucial. Developing improved materials continues advancing quantum computing hardware. Scaling considerations determine how quantum computing systems can grow to practically useful sizes. Different platforms face distinct scaling challenges in areas like control complexity, error rates, and manufacturing. Understanding these scaling limits guides platform development. Test and characterization methods enable assessment of quantum device performance. Developing efficient testing protocols while maintaining quantum coherence poses ongoing challenges. Effective testing remains crucial for developing improved quantum hardware. The interplay between hardware capabilities and algorithm development shapes quantum computing progress. Hardware limitations influence algorithm design, while algorithmic requirements guide hardware development. This cooperative evolution continues advancing quantum computing technology. Manufacturing considerations become increasingly important as quantum computers scale. Developing reliable, cost-effective production methods while maintaining device quality presents ongoing challenges. Addressing manufacturing challenges remains crucial for practical quantum computing. These various aspects of quantum computing hardware continue evolving as the field progresses toward practical quantum computers. Success requires advances across multiple technological fronts while maintaining quantum coherence and computational fidelity. The ongoing development of quantum hardware drives progress toward practical quantum computation. Quantum metrology exploits quantum mechanical effects to achieve measurement precision beyond classical limits. These techniques use quantum states, particularly entangled and squeezed states, to enhance measurement sensitivity in applications ranging from atomic clocks to gravitational wave detection. The standard quantum limit represents the measurement precision achievable with classical resources. Quantum metrology can surpass this limit, approaching the Heisenberg limit, the ultimate bound on measurement precision allowed by quantum mechanics. This quantum advantage emerges from the unique properties of quantum states and measurements. Atomic clocks provide a prime example of quantum metrology in action. By exploiting quantum superposition states in atoms, these clocks achieve unprecedented timing precision. Modern atomic clocks lose less than 1 second over billions of years, enabling applications from GPS navigation to fundamental physics tests. Quantum sensors leverage quantum effects for enhanced detection capabilities. Nitrogen vacancy centers in diamond serve as quantum magnetometers, detecting minute magnetic fields with nanoscale spatial resolution. These sensors find applications in materials, science, biology, and medical imaging. Gravitational wave detection demonstrates quantum metrology at a massive scale. Advanced detectors use squeezed light states to enhance sensitivity beyond the standard quantum limit. This quantum enhancement helps detect gravitational waves from cosmic events billions of light years away. Quantum imaging techniques exploit quantum correlations to achieve resolution beyond classical diffraction limits. Ghost imaging uses entangled photon pairs to create images without directly detecting photons that interact with the object. These methods enable new approaches to microscopy and remote sensing. Quantum gyroscopes utilize matter wave interference to measure rotation with extraordinary precision. These devices exploit quantum coherence in atom interferometers, offering potential improvements over classical gyroscopes for navigation and geodesy applications. The development of quantum-enhanced measurement protocols requires careful consideration of quantum resource requirements. Different measurement strategies optimize the trade-off between quantum resource consumption and measurement precision. Understanding these trade-offs guides practical sensor design. Environmental noise poses significant challenges for quantum sensors. Quantum error correction and dynamical decoupling techniques help protect quantum states from decoherence while maintaining measurement sensitivity. Balancing protection and measurement strength remains crucial for practical applications. Networked quantum sensors enable distributed sensing applications. Quantum entanglement between separate sensors can enhance measurement precision and enable new sensing modalities. These networks could provide unprecedented capabilities for environmental monitoring and navigation. Quantum feedback control improves sensor performance through real-time measurement and adjustment. Adaptive measurement protocols optimize sensing parameters based on measurement results. These techniques enhance measurement precision while reducing resource requirements. The integration of quantum sensors with classical systems requires careful interface design. Converting quantum measurements to classical signals while preserving measurement advantages poses ongoing challenges. Effective interfaces remain crucial for practical quantum sensing applications. Quantum illumination enables enhanced target detection in noisy environments. By exploiting quantum correlations between probe and reference signals, these techniques achieve better signal-to-noise ratios than classical methods. Applications include radar and biological sensing. The relationship between measurement precision and quantum resource consumption reveals fundamental physical limits. The quantum Cramér-Rao bound establishes ultimate limits on measurement precision for given quantum resources. Understanding these limits guides quantum sensor optimization. Practical implementations of quantum sensors face various technical challenges. Maintaining quantum coherence while enabling precise measurement access requires sophisticated engineering. Addressing these challenges drives ongoing technology development. Quantum sensing applications continue expanding across different fields. From medical diagnostics to geological surveying, quantum sensors offer new measurement capabilities. Understanding application requirements guides sensor development. The connection between quantum sensing and fundamental physics enables new tests of physical theories. Precise measurements can probe quantum mechanics, general relativity, and their intersection. These experiments advance both practical technology and basic science. Quantum sensor networks enable new approaches to navigation and timing. Distributed quantum sensors could provide robust positioning systems independent of satellite signals. Development of these networks continues advancing quantum technology applications. Manufacturing considerations become increasingly important as quantum sensors move toward practical applications. Developing reliable, cost-effective production methods while maintaining device performance presents ongoing challenges. Addressing these challenges remains crucial for practical quantum sensing. The future of quantum metrology promises continued advances in measurement precision and applications. As quantum technologies mature, new sensing capabilities emerge. Ongoing development drives progress toward practical quantum-enhanced measurements while deepening our understanding of quantum measurement fundamentals. Quantum communication exploits quantum mechanical principles for secure information transmission. Unlike classical communication, quantum channels use individual quantum systems as information carriers, enabling protocols with security guaranteed by physical laws rather than computational complexity. Quantum key distribution, QKD, represents the most developed quantum communication protocol, enabling two parties to generate shared secret keys with provable security. The BB84 protocol, using single photon polarization states, demonstrates how quantum mechanics prevents undetected eavesdropping through the no-cloning theorem and measurement disturbance. Entanglement-based protocols extend QKD capabilities through quantum correlations. The E91 protocol uses entangled photon pairs to generate secure keys while simultaneously verifying the absence of eavesdropping. These protocols highlight connections between fundamental quantum mechanics and practical security. Quantum repeaters address distance limitations in quantum communication networks. Unlike classical repeaters. Quantum repeaters must preserve quantum states without direct measurement, using entanglement swapping and quantum memories. Development of practical quantum repeaters continues advancing quantum network technology. Quantum Internet protocols enable distributed quantum information processing. These networks support applications from secure communication to distributed quantum computing. Protocol development addresses challenges in quantum state distribution and network routing. Device-independent quantum cryptography removes assumptions about implementation hardware. These protocols remain secure even with untrusted devices, verified through Bell inequality violations. This approach provides strongest security guarantees while requiring more resources. Continuous variable quantum cryptography uses quantum states with continuous degrees of freedom. These protocols offer practical advantages through established telecommunications technology while maintaining security. Implementation requires careful management of noise and loss. Quantum digital signatures provide unforgeable message authentication using quantum mechanics. These protocols extend classical digital signatures with quantum security guarantees. Development continues improving efficiency and practical implementation. Quantum secret sharing enables secure distribution of quantum information among multiple parties. These protocols extend classical secret sharing while preserving quantum properties. Applications include distributed quantum computing and secure multi-party computation. Quantum memory development remains crucial for quantum communication networks. These devices must store quantum states while maintaining coherence and allowing controlled retrieval. Various physical implementations compete to achieve practical quantum memories. Error correction in quantum communication addresses noise and loss effects. Quantum error correction codes protect transmitted quantum information while enabling practical implementation. Development continues improving code efficiency and hardware requirements. Authentication protocols ensure genuine quantum communication channels. These protocols prevent man-in-middle attacks while maintaining quantum security advantages. Integration with classical authentication systems enables practical implementation. Quantum random number generation provides true randomness for cryptographic applications. These systems exploit quantum uncertainty for unpredictable number generation. Applications include key generation and secure random sampling. Implementation challenges include maintaining quantum coherence during transmission. Fiber optic networks and free space links require careful engineering to preserve quantum states. Addressing these challenges enables practical quantum communication. Security analysis of quantum communication protocols requires careful consideration of implementation vulnerabilities. Side-channel attacks exploit hardware imperfections rather than protocol weaknesses. Understanding and mitigating these vulnerabilities remains crucial. Network architecture for quantum communication differs fundamentally from classical networks. Quantum routing and switching must preserve quantum states while enabling network flexibility. Development continues advancing quantum network capabilities. Integration with existing communication infrastructure enables practical deployment. Hybrid classical quantum networks leverage existing fiber optic networks while maintaining quantum security advantages. This approach facilitates gradual quantum network deployment. Standardization efforts establish common protocols for quantum communication systems. These standards enable interoperability between different implementations while maintaining security requirements. Development continues through international collaboration. Commercial applications of quantum communication emerge as technology matures. Financial institutions and government agencies implement quantum security solutions. Market development drives continued technology advancement. The future of quantum communication promises enhanced security and new capabilities. Ongoing development addresses technical challenges while expanding applications. Progress continues toward practical quantum communication networks. Quantum thermodynamics extends classical thermodynamics to quantum systems, revealing new phenomena and limitations at the microscopic scale. Quantum heat engines and refrigerators operate using quantum resources, potentially achieving efficiencies beyond classical bounds. Single-atom heat engines demonstrate fundamental quantum thermodynamic principles. These microscopic engines use quantum states and coherences to convert heat into work. Their operation reveals quantum effects in energy conversion and thermodynamic processes. Quantum coherence provides additional resources for thermodynamic processes. Unlike classical systems, quantum coherence enables new pathways for energy conversion and heat transfer. Understanding these quantum advantages guides development of efficient quantum thermal devices. The relationship between quantum information and thermodynamics reveals fundamental connections. Landauer's principle links information erasure to energy dissipation at the quantum level. These connections illuminate the physical nature of information processing. Quantum fluctuation theorems extend classical fluctuation relations to quantum systems. These theorems describe energy fluctuations and entropy production in quantum processes. They provide framework for understanding quantum thermodynamic processes. Work extraction from quantum systems requires careful consideration of measurement and control. Quantum measurements affect system states, influencing available work. Protocols must balance information gain against disturbance. Quantum thermal machines operate between quantum heat reservoirs. Their performance depends on quantum properties of working substances and reservoirs. Design must account for quantum effects in heat transfer and work extraction. The third law of thermodynamics takes new forms in quantum systems. Quantum effects modify how systems approach absolute zero temperature. Understanding these modifications guides low-temperature quantum device operation. Quantum refrigeration faces unique challenges and opportunities. Quantum coherence and entanglement enable novel cooling mechanisms. These quantum effects suggest new approaches to achieving ultra-low temperatures. Energy transport in quantum systems shows distinct features from classical transport. Quantum coherence and interference affect energy flow patterns. Understanding these effects enables better thermal management in quantum devices. Quantum thermalization describes how isolated quantum systems reach equilibrium. The eigenstate thermalization hypothesis provides framework for understanding this process. These insights guide quantum device design and operation. Maxwell's demon thought experiment gains new perspectives in quantum systems. Quantum measurement and feedback enable new demon implementations. These studies reveal connections between information and thermodynamics. Quantum batteries store energy using quantum states. Charging and discharging processes exploit quantum effects for enhanced performance. Development continues improving energy density and charging speeds. The quantum Otto cycle provides quantum analog of classical Otto cycle. This cycle demonstrates quantum effects in cyclic processes. Analysis reveals quantum advantages in thermal machine operation. Quantum thermal transistors control energy flow using quantum effects. These devices enable new approaches to thermal management. Applications include quantum computing and precision measurement. Heat flow control at quantum scale enables new device capabilities. Quantum thermal rectifiers and switches exploit quantum effects. These components support quantum thermal circuit development. Quantum thermometric precision reveals fundamental measurement limits. Quantum effects modify temperature measurement capabilities. Understanding these limits guides quantum thermometer development. Experimental implementations face various technical challenges. Maintaining quantum effects while enabling thermal operation requires careful design. Addressing these challenges drives ongoing technology development. The relationship between quantum thermodynamics and quantum computing reveals practical implications. Thermal management affects quantum computer operation. Understanding quantum thermodynamics guides cooling system design. Future quantum thermal technologies promise new capabilities in energy conversion and thermal management. Ongoing development addresses technical challenges while expanding applications. Progress continues toward practical quantum thermal devices. The measurement problem in quantum mechanics remains a central challenge in quantum foundations. Different interpretations propose various resolutions to how quantum superpositions become definite measurement outcomes, each with distinct philosophical implications about reality's nature. Copenhagen interpretation, historically dominant, posits fundamental roles for measurement and classical concepts. It treats quantum mechanics as a tool for predicting measurement outcomes rather than describing underlying reality. The interpretation emphasizes pragmatic utility while leaving philosophical questions largely unanswered. Many worlds interpretation eliminates wave function collapse by suggesting reality contains all possible measurement outcomes. Each measurement outcome occurs in a different branch of an ever-branching universe. This interpretation preserves quantum mechanics' unitarity, but raises questions about probability and identity. Pilot wave theory maintains deterministic particle trajectories guided by real wave functions. This interpretation achieves determinism and realism, but requires non-local interactions. It demonstrates possibility of deterministic quantum mechanics while challenging locality assumptions. Quantum Bayesianism, cubism, treats quantum states as representations of knowledge rather than physical reality. This interpretation connects quantum mechanics to probability theory and subjective knowledge. It resolves measurement paradoxes while raising questions about physical reality's nature. Consistent history's interpretation focuses on sequences of events rather than instantaneous states. It provides framework for discussing quantum systems' temporal evolution without invoking measurement collapse. This approach addresses temporal aspects of quantum mechanics often overlooked. Decoherence theory explains emergence of classical behavior from quantum systems. Environmental interactions effectively measure quantum systems, causing apparent wave function collapse. This mechanism bridges quantum and classical descriptions while leaving interpretational questions open. Relational interpretation suggests quantum states describe relationships between systems rather than absolute properties. This view connects to special relativity's relational nature while offering new perspective on measurement problem. Modal interpretations attempt to assign definite properties to quantum systems while maintaining quantum mechanics' mathematical structure. These interpretations explore possible property assignments consistent with quantum formalism. Objective collapse theories propose physical mechanisms for wave function collapse. These modifications to quantum mechanics make collapse objective rather than measurement dependent. Such theories offer testable predictions, differing from standard quantum mechanics. Information theoretic approaches investigate quantum mechanics foundations through information concepts. These perspectives illuminate connections between quantum theory and information processing. They suggest fundamental role for information in physical reality. Contextuality reveals quantum systems' properties depend on measurement context. This feature distinguishes quantum from classical physics while constraining possible interpretations. Understanding contextuality aids quantum technology development. Hidden variable theories explore whether quantum mechanics' probabilistic nature reflects underlying deterministic dynamics. Bell's theorem constrains possible hidden variable theories through experimentally testable predictions. Quantum logic investigates alternative logical structures for quantum mechanics. These approaches suggest quantum phenomena require modifying classical logic. They provide mathematical framework for understanding quantum superposition and interference. Time symmetry in quantum mechanics raises questions about causality and retrocausality. Various interpretations handle temporal aspects differently, affecting views on free will and determinism. Observer role in quantum mechanics connects to consciousness and reality questions. Different interpretations assign various roles to observation and consciousness, affecting philosophical implications. Experimental tests continue probing quantum mechanics foundations. While interpretations make identical standard predictions, some suggest subtle differences, testable with advanced experiments. Practical implications emerge from foundational investigations. Understanding quantum foundations guides quantum technology development while revealing fundamental physical principles. Quantum reconstruction programs attempt deriving quantum mechanics from simple principles. These approaches seek deeper understanding of why quantum mechanics takes its observed form. Future developments in quantum foundations may resolve long-standing puzzles while revealing new insights about reality's nature. Progress continues through theoretical analysis and experimental investigation. Loop quantum gravity proposes discrete quantized structure of space-time at Planck scale. This theory maintains background independence while quantizing general relativity's geometrical properties. Space becomes granular, composed of fundamental units called spin networks. String theory suggests fundamental objects are one-dimensional strings vibrating in multiple dimensions. These vibrations generate observed particles and forces, including gravity. Extra dimensions, compactified beyond observation, enable theory's mathematical consistency. Asymptotic safety scenario proposes quantum gravity might be non-perturbatively renormalizable. This approach suggests gravitational coupling strength becomes finite at high energies, avoiding infinities plaguing other approaches. Causal dynamical triangulations construct space-time from discrete four-dimensional building blocks. Computer simulations demonstrate emergence of classical space-time features from quantum constituents. This approach provides numerical insight into quantum gravity. Causal set theory discretizes space-time into partially ordered sets of events. This approach maintains Lorentz invariance while suggesting fundamental discreteness. Quantum dynamics emerges from causal relationships between events. Group field theory reformulates quantum gravity as quantum field theory on group manifolds. This framework connects loop quantum gravity with field theoretical methods. It suggests space-time emerges from more fundamental degrees of freedom. Holographic principle suggests quantum gravity theories in space-time correspond to quantum theories on boundary. This principle, inspired by black hole physics, provides constraints on possible quantum gravity theories. Non-commutative geometry approaches quantum gravity through modified mathematical frameworks. These theories suggest quantum effects make space-time coordinates non-commutative at small scales. Quantum geometrodynamics attempts direct quantization of Einstein's equations. Wheeler-DeWitt equation describes quantum state of gravitational field. This approach faces technical and conceptual challenges. Modified gravity theories explore alternatives to general relativity compatible with quantum mechanics. These approaches range from simple modifications to radical reformulations of gravitational theory. Experimental tests of quantum gravity theories remain challenging due to enormous energy scales involved. Indirect tests through cosmological observations and precision measurements guide theory development. Quantum gravity phenomenology studies potentially observable effects of quantum gravity. These include modified dispersion relations and violations of Lorentz invariance at high energies. Black hole physics provides crucial testing ground for quantum gravity theories. Explaining black hole entropy and resolving information paradox guide theoretical development. Cosmological singularity resolution requires quantum gravity understanding. Different approaches suggest various mechanisms for avoiding Big Bang singularity. Emergence of classical spacetime from quantum gravity remains a crucial challenge. Understanding this transition illuminates relationship between quantum and classical gravity. Unification with other forces represents major goal for quantum gravity theories. Different approaches propose various mechanisms for incorporating other interactions. Mathematical frameworks for quantum gravity require sophisticated tools. Development of mathematical methods continues advancing theoretical understanding. Practical implications emerge despite enormous energy scales involved. Understanding quantum gravity influences other areas of physics and technology development. Cosmological singularity resolution requires quantum gravity understanding. Different approaches suggest various mechanisms for avoiding Big Bang singularity. Emergence of classical space-time from quantum gravity remains a crucial challenge. Understanding this transition illuminates relationship between quantum and classical gravity. Unification with other forces represents major goal for quantum gravity theories. Different approaches propose various mechanisms for incorporating other interactions. Mathematical frameworks for quantum gravity require sophisticated tools. Development of mathematical methods continues advancing theoretical understanding. Practical implications emerge despite enormous energy scales involved. Understanding quantum gravity influences other areas of physics and technology development. Philosophical implications about space, time, and causality arise from quantum gravity theories. Different approaches suggest various pictures of fundamental reality. Future developments may resolve competing approaches while revealing deeper understanding of quantum gravity. Progress continues through theoretical and observational advances. Quantum cosmology applies quantum mechanics to the entire universe, addressing fundamental questions about cosmic origins and evolution. The Wheeler-DeWitt equation describes universe's quantum state, suggesting timeless nature of quantum cosmos. Inflationary cosmology gains new perspective through quantum effects. Quantum fluctuations during inflation seed cosmic structure formation. These quantum origins explain observed galaxy distribution and cosmic microwave background patterns. Wave function of the universe describes quantum state of entire cosmos. This universal wave function evolves according to Wheeler-DeWitt equation, raising questions about time's role in quantum universe. Quantum bounce models suggest Big Bang singularity resolves into quantum transition from previous universe. Various approaches propose different mechanisms for this bounce. Avoiding classical singularity, eternal inflation emerges from quantum effects in expanding universe. Quantum fluctuations drive continuous creation of new universe regions. This process generates infinite multiverse of diverse cosmic domains. Third quantization treats universe creation and destruction through quantum field theory framework. Universe wave functions become operators creating and annihilating universes. This approach provides mathematical structure for multiverse theories. Decoherence in early universe explains emergence of classical space-time. Environmental interactions select preferred classical configurations from quantum superpositions. This mechanism bridges quantum and classical cosmological descriptions. Quantum cosmological perturbation theory describes structure formation from quantum fluctuations. This framework connects quantum mechanical origins with observed cosmic structures. Holographic cosmology suggests early universe description through lower dimensional quantum theory. This approach connects string theory insights with cosmological observations. Quantum gravity effects dominate universe near Planck time. Different quantum gravity approaches suggest various pictures of earliest cosmic moments. Vacuum energy receives quantum corrections affecting cosmic evolution. Understanding these corrections helps address cosmological constant problem. Matter-antimatter asymmetry might originate from quantum effects in early universe. Various mechanisms propose quantum origin for observed matter dominance. Cosmic topology connects with quantum gravitational effects. Universe's large-scale structure might reflect quantum geometric properties. Initial conditions problem gains new perspective through quantum cosmology. Quantum effects might naturally explain observed universe properties. Observational tests of quantum cosmology remain challenging, but possible. Cosmic, microwave background, and large-scale structure provide evidence of quantum origins. Time problem in quantum cosmology raises fundamental questions about temporal evolution. Various approaches propose different resolutions to apparent timelessness. Multiverse theories gain support from quantum cosmological considerations. Different approaches suggest various mechanisms for multiple universe creation. Arrow of time emerges from quantum cosmological considerations. Decoherence and entropy increase connect with quantum to classical transition. Anthropic principles take new form in quantum cosmological context. Observer role in quantum mechanics connects with cosmic habitability questions. Future observations may reveal more direct evidence of universe's quantum origins. Gravitational wave astronomy and precision cosmology advance understanding. Quantum field theory in curved space-time examines quantum effects in gravitational fields. Standard quantum field theory requires modification in curved backgrounds, revealing new phenomena like Hawking radiation and particle creation in expanding universe. Vacuum states become observer-dependent in curved space-time. Different observers disagree about particle content, challenging particle concept's universality. Unruh effect demonstrates accelerated observers detect particles in vacuum. Particle creation occurs in dynamical space-times. Expanding universe creates particles from vacuum fluctuations. This process contributes to cosmic particle content and early universe dynamics. Hawking radiation emerges from quantum fields near black holes. Event horizon creates particle-antiparticle pairs, leading to black hole evaporation. This process connects quantum mechanics, gravity, and thermodynamics. Renormalization requires modification in curved backgrounds. Standard techniques face new challenges from space-time curvature. Modified approaches handle infinities while maintaining physical predictions. Back reaction of quantum fields affects space-time geometry. Quantum fluctuations modify Einstein equations through stress-energy tensor. Understanding these effects remains crucial for quantum gravity. Cosmological particle production influences universe evolution. Created particles contribute to cosmic energy density. This process affects early universe dynamics and structure formation. Mode functions in curved space-time determine particle content. Different observers decompose fields differently, leading to particle ambiguity. Understanding these decompositions clarifies particle concept. Energy conditions face modification from quantum effects. Classical energy conditions break down at quantum level. Modified conditions incorporate quantum corrections while maintaining physical consistency. Stress-energy tensor receives quantum corrections. Vacuum polarization modifies classical stress energy. These corrections influence space-time dynamics through Einstein equations. Black hole thermodynamics emerges from quantum field effects. Temperature and entropy gain quantum mechanical origin. This connection illuminates relationships between gravity and thermodynamics. Singularity theorems require modification from quantum effects. Classical singularity theorems break down at quantum level. Quantum corrections might prevent singularity formation. Information paradox connects to field behavior near horizons. Quantum field entanglement affects information preservation. Understanding these effects helps resolve black hole puzzles. Vacuum polarization affects black hole properties. Quantum corrections modify classical black hole parameters. These effects influence black hole evolution and thermodynamics. Cosmological constant receives quantum contributions. Vacuum energy density includes quantum field effects. Understanding these contributions addresses cosmological constant problem. Modified dispersion relations emerge at high energies. Quantum gravity effects alter particle propagation. These modifications might provide observational tests. Entanglement structure depends on space-time geometry. Curved space-time affects quantum correlations. Understanding these relationships advances quantum gravity understanding. Experimental tests remain challenging but possible. Analog systems simulate curved space-time effects. Laboratory experiments provide indirect tests of theoretical predictions. Theoretical developments continue advancing understanding. New mathematical tools handle curved space-time complexities. Progress improves quantum gravity insights. Future research promises deeper understanding of quantum fields in gravity. Observational advances may provide direct tests. Development continues revealing nature's fundamental structure. Quantum decoherence explains emergence of classical behavior from quantum systems through environmental interactions. Wave function entanglement with environment effectively measures quantum states, causing apparent collapse into classical states without modifying quantum mechanics. Environmental monitoring occurs through uncontrolled interactions, spreading quantum correlations. Each interaction encodes system information in environment, making quantum superpositions effectively classical. This process happens extremely rapidly for macroscopic objects. Phase relationships between quantum states become effectively random through environmental interaction. Interference effects, characteristic of quantum behavior, disappear locally while remaining preserved in larger system environment state. Preferred states emerge through interaction with environment. Certain states remain stable, while others rapidly decohere. This selection process explains why we observe particular classical states. Quantum Darwinism describes how environmental interactions replicate system information. Multiple observers can access same classical information about quantum system. This process explains objective reality's emergence. Measurement problem receives natural explanation through decoherence. No fundamental collapse occurs. Environment continuously measures quantum systems. This view maintains quantum mechanics unitarity while explaining classical appearances. Classical limit emerges dynamically through decoherence process. Quantum to classical transition occurs gradually as system size increases. Understanding this transition guides quantum technology development. Pointer states survive environmental interaction while superpositions decay. These robust states form basis for classical behavior. Selection process depends on system-environment interaction form. Information transfer to environment occurs irreversibly for practical purposes. While quantum mechanics remains reversible, environmental complexity makes reversal practically impossible. Time scales for decoherence depend on system size and environmental coupling. Microscopic systems maintain coherence longer than macroscopic ones. Understanding these scales guides quantum device design. Spatial localization emerges through decoherence. Environmental interactions select position-based states. This process explains why macroscopic objects appear localized. Quantum correlations spread through environment at finite speed. Information about quantum system propagates causally. This process respects special relativity while explaining classical behavior. Experimental observation of decoherence provides direct evidence for theory. Controlled decoherence studies reveal transition mechanisms. These experiments guide quantum technology development. Quantum computing requires protection from decoherence. Error correction and environmental isolation preserve quantum information. Understanding decoherence guides protection strategies. Classical records emerge through environmental encoding. Multiple observers agree on classical properties through shared environmental information. This process explains objective reality's emergence. Entropy increase connects with decoherence process. Information spread through environment increases entropy. This connection explains arrow of time's emergence. Practical applications emerge from decoherence understanding. Quantum device design requires managing environmental interactions. This knowledge advances quantum technology development. Philosophical implications arise from decoherence theory. No fundamental quantum classical boundary exists. Transition occurs gradually. This view affects interpretation of quantum mechanics. Future research continues revealing decoherence details. Improved understanding guides quantum technology development. Progress advances fundamental physics understanding. Theoretical developments refine decoherence models. New mathematical tools handle complex environmental interactions. Understanding improves quantum to classical transition picture. Quantum coherent control manipulates quantum systems through precise external fields. Time-dependent controls guide quantum evolution for information processing, sensing, and spectroscopy applications. Understanding control mechanisms enables quantum technology development. Optimal control theory provides framework for designing control pulses. Numerical optimization finds pulse sequences, achieving desired quantum operations. These techniques balance control fidelity against practical constraints. Robust control methods handle uncertainties in system parameters. Control designs maintain performance despite imperfect system knowledge. This robustness proves crucial for practical applications. Feedback control incorporates measurement results into control strategy. Real-time adjustments compensate for errors and disturbances. Quantum feedback faces unique challenges for measurement effects. Geometric quantum control exploits systems' mathematical structure. Control operations utilize geometric phases and holonomies. These approaches offer robust control alternatives. Selective excitation techniques address specific quantum transitions. Shaped pulses target desired states while avoiding others. Applications include quantum computing and spectroscopy. Decoherence-free control preserves quantum information despite environmental coupling. Control sequences minimize decoherence effects. These methods extend quantum coherence times. Open-loop control sequences work without measurement feedback. Pre-designed pulse sequences achieve desired operations. This approach avoids measurement complications. Closed-loop control incorporates continuous measurement feedback. Real-time adjustments optimize system performance. Technical challenges include measurement speed and precision. Quantum reservoir engineering shapes system-environment interaction. Engineered environments enable desired quantum dynamics. Applications include quantum state preparation. Multi-qubit control addresses quantum register manipulation. Parallel operations maintain quantum coherence. Scaling challenges increase with system size. Quantum error correction requires precise control operations. Error detection and correction maintain quantum information. Control fidelity determines correction effectiveness. Control hardware limitations constrain achievable operations. Finite bandwidth and precision affect control quality. Understanding limitations guides control design. Experimental implementations face various technical challenges. Hardware imperfections affect control performance. Addressing these challenges advances practical applications. Time-optimal control minimizes operation duration. Faster operations reduce decoherence effects. Mathematical techniques find optimal trajectories. State preparation and measurement require precise control. Initial state quality affects subsequent operations. Measurement precision influences control effectiveness. Control verification ensures operation quality. Diagnostic techniques assess control performance. Verification guides control improvement. Future developments promise improved control capabilities. Advanced hardware enables precise manipulation. Progress continues advancing quantum technology. Theoretical understanding guides practical implementation. Mathematical frameworks inform control design. Development combines theory and experiment. Applications span quantum computing, sensing, and spectroscopy. Control techniques enable various quantum technologies. Progress advances practical capabilities. Quantum technologies translate fundamental quantum mechanics into practical applications. Current developments span computing, communication, sensing, and simulation. These advances promise revolutionary capabilities across multiple fields. Quantum computing approaches practical implementation through various platforms. Superconducting circuits, trapped ions, and other systems demonstrate basic operations. Scaling challenges remain while algorithms advance. Quantum communication networks enable secure information transmission. Quantum key distribution provides theoretically unbreakable encryption. Global quantum networks approach reality. Quantum sensors achieve unprecedented measurement precision. Atomic clocks, magnetometers, and gravitational sensors exploit quantum effects. Applications span navigation, medical imaging, and scientific research. Quantum simulation addresses complex quantum system modeling. Controlled quantum systems simulate material properties and chemical reactions. These capabilities advance scientific understanding. Error correction implementation progresses toward fault tolerance. Various codes protect quantum information from noise. Hardware improvements reduce error rates. Quantum software development creates tools for quantum systems. Programming frameworks and optimization techniques advance. Software ecosystems grow with hardware capabilities. Integration with classical systems enables practical applications. Hybrid quantum classical approaches leverage both technologies. This integration facilitates gradual adoption. Commercial quantum technology markets continue expanding. Investment drives development across multiple sectors. Applications diversify as capabilities improve. International competition accelerates quantum technology development. National programs invest in research and development. Strategic implications drive continued advancement. Standardization efforts establish common protocols and interfaces. Industry collaboration enables technology integration. Standards support market development. Educational programs prepare quantum technology workforce. Universities develop quantum engineering programs. Training advances technical capabilities. Ethical considerations guide technology development and deployment. Security implications require careful consideration. Responsible development ensures beneficial applications. Research continues advancing fundamental understanding. New quantum phenomena suggest novel applications. Theory and experiment progress together. Manufacturing capabilities advance toward production scale. Fabrication techniques improve device quality. Cost reduction enables broader adoption. System integration challenges receive increasing attention. Complex quantum systems require careful engineering. Solutions advance practical implementation. Verification and validation methods ensure reliable operation. Testing protocols confirm system performance. Quality control enables practical deployment. Future applications continue emerging across fields. Quantum technology impacts various industries. Development expands capability boundaries. Technical challenges drive continued innovation. Solutions advance fundamental capabilities. Progress enables new applications. Quantum technology's future promises revolutionary capabilities while requiring continued development. Success demands advances across multiple fronts. Progress continues through theoretical and practical innovation. Up next, you've got two more standout theory right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.